Picture holding a single grain of sand between your fingers. Tiny, insignificant, barely noticeable. Now, imagine that grain is our entire Milky Way galaxy, home to hundreds of billions of stars, countless planets, and everything we've ever known. Staggering, right? But here's where it gets mind-blowing. The largest structures in the universe make our galaxy look like that speck of sand beside an endless, sprawling beach. These cosmic behemoths stretch across unimaginable distances, defying logic and rewriting everything we thought we knew about space. Today, we're embarking on a journey to uncover 50 astonishing facts about these colossal formations, structures so vast, their sheer scale bends the mind. From walls of galaxies stretching billions of light years to mysterious voids where nothing seems to exist, the universe holds secrets that challenge our very understanding of reality. What does it even mean for something to be large in a cosmos where distances are measured in millions, even billions of light years? Think about this. Light, the fastest thing in existence, takes 100,000 years just to cross our galaxy. Yet, some of these titanic structures are so enormous that light would need tens of billions of years to travel from one end to the other. They're not just bigger than anything we've ever seen, they're bigger than anything we've ever dreamed. And the wildest part, we don't fully understand how they formed. These are not just random clumps of matter, they're intricate, organized, and eerily deliberate, as if the universe itself decided to paint its masterpiece on a canvas too vast for us to comprehend. This isn't just a story about size. It's about mystery, about discovery, about the human drive to reach beyond what we know and touch the edges of the unknown. Every fact we uncover peels back another layer of the cosmos, revealing questions far more profound than the answers we find. So, as we dive into these 50 mind-bending revelations, prepare to have your sense of scale shattered, your curiosity ignited, and your place in the universe redefined. Because out there, in the darkness between the stars, lies a reality so immense, so extraordinary, it makes our world feel like a single grain of sand in an endless cosmic ocean. And we're just beginning to explore it. If our universe had a skeleton, it would look something like the cosmic web, an intricate, sprawling network of galaxies and dark matter stretching across unfathomable distances. Picture a spider's silk, but spun on a scale so vast that a single thread could contain thousands of galaxies, each one a glowing speck in the darkness. This isn't science fiction, it's the very fabric of our reality, the hidden architecture that shapes everything we see. Scientists call it the largest known structure in existence, a cosmic blueprint that emerged just moments after the Big Bang, when tiny ripples in the newborn universe began pulling matter into vast, thread-like chains. But how do you map something so enormous that it defies human intuition? The answer lies in starlight specifically, the light from quasars, some of the brightest objects in the cosmos. These celestial beacons shine through the cosmic web like headlights piercing fog, their light absorbed slightly by the gases strung along the filaments. By studying these subtle dimming patterns, astronomers have slowly pieced together a three-dimensional map of this colossal structure, revealing a web so vast it takes light billions of years to traverse it. And here's the eerie part, what we're seeing is just the visible scaffolding. The cosmic web is mostly woven from dark matter, the mysterious, invisible substance that makes up nearly 85% of the universe's mass. Without it, galaxies would never have clumped together. Stars would drift apart like lonely ships in an endless sea. This delicate balance, gravity pulling matter into threads, dark matter anchoring it all, creates the cosmic stage where galaxies dance in clusters, connected by bridges of gas and mystery. It's a reminder that even the grandest structures in existence are built from forces we're only beginning to understand. Now, let's zoom in on one of the most jaw-dropping structures in the known universe, the Great Wall, also called the Hercules-Corona Borealis Great Wall. This isn't just big, it's universe-breaking big. Imagine a colossal assembly of galaxies, a filament stretching an almost incomprehensible 10 billion light-years from end to end. To put that into perspective, if you could travel at the speed of light, it would take you twice the age of Earth just to cross it. This isn't merely a cluster or a supercluster. It's a cosmic metropolis, a sprawling, interconnected network of galactic neighborhoods so vast that its existence defies some of our most fundamental cosmological principles. Scientists stumbled upon this behemoth not by spotting the galaxies themselves, but by tracing something far more fleeting: gamma-ray bursts. These are the universe's most violent explosions, the death cries of massive stars collapsing into black holes or neutron stars. They flare up for mere seconds, but their brilliance makes them visible across staggering distances. Researchers noticed something odd. These bursts weren't randomly scattered. They clustered in a pattern too vast and too structured to be coincidence. Mapping them revealed a gargantuan wall of galaxies, a cosmic architecture so immense it shouldn't exist according to the cosmological principle, which states that matter should be spread roughly evenly across the universe on the largest scales. Here's the puzzle: structures this big shouldn't have had enough time to form after the Big Bang. Gravity works slowly, tugging matter together over eons. Yet the Great Wall's existence suggests that either our understanding of cosmic evolution is incomplete, or the universe played by different rules in its infancy. Some theories propose exotic ideas like early dark energy accelerating structure formation, or primordial quantum fluctuations seeding these titanic imbalances in the newborn cosmos. What makes this discovery even more astonishing is how it reshapes our cosmic perspective. We once thought superclusters were the pinnacle of largeness, but the Great Wall dwarfs them all. It's not just an object, it's a boundary, a seam in the fabric of space where the universe decided to gather its material into something monumental, and the strangest thought of all. This might not even be the biggest structure out there. It's just the largest one we've confirmed so far. In the endless expanse of the cosmos, there may be walls beyond walls, structures so vast they make the Great Wall look like a wrinkle in the universe's skin. That's the humbling beauty of space. Every time we think we've found the limit, the cosmos reveals another layer of its grandeur. Before the Hercules-Corona Borealis Great Wall shattered size records, there was the Sloan Great Wall, a staggering ribbon of galaxies stretching 1.4 billion light-years across the cosmos. Discovered in 2003 by mapping millions of galaxies in the Sloan Digital Sky Survey, this cosmic leviathan held the title of largest known structure for over a decade. But its grandeur isn't just in its length, it's in its peculiar shape. Unlike newer filamentary discoveries that twist through space like tangled strands, the Sloan Great Wall is flat, almost like a colossal pancake floating in the void, with superclusters layered across its surface like glitter scattered on a table. What makes this structure so fascinating is how it formed. Gravity works like a cosmic sculptor, pulling matter into clusters over billions of years. But the Sloan Wall's unusual flatness suggests something special happened in this region. Perhaps an ancient ripple in the density of the early universe, a fluctuation so vast it set the stage for this gargantuan sheet of galaxies. Picture dropping a pebble into a pond, but instead of rings fanning outward, the ripples freeze into a single, sprawling plane of matter. Yet even this titan has been overshadowed by newer discoveries. The Sloan Wall's pancake shape, while impressive, lacks the intricate branching of the cosmic web or the mind-bending scale of the Hercules-Corona Borealis structure. It's a reminder of how quickly our understanding of the universe evolves. What once seemed impossibly large is now just another thread in the tapestry. But don't let that diminish its wonder. The Sloan Great Wall still dwarfs anything in our galactic neighborhood. If our Milky Way were a single house, this structure would be an entire continent, with superclusters as cities and galaxy filaments as highways connecting them. And here's the haunting thought: we're seeing it as it was over 1 billion years ago, its light just now reaching us. the actual structure may have stretched, twisted, or even dispersed by now, leaving behind this ghostly imprint of its ancient self. That's the paradox of cosmic exploration. We're always peering into the past, uncovering fragments of a story still being written. The Sloan Great Wall isn't just a relic of scale, it's a monument to our relentless curiosity, proof that every record we set is just a placeholder until the universe reveals something even grander. We think of the Milky Way as vast, our galactic home spinning through the darkness, but zoom out far enough and you'll see we're just a speck in something far grander. The Laniakea supercluster, a sprawling celestial continent 520 million light-years across. The name comes from Hawaiian, meaning immeasurable heaven, and it's no exaggeration. Picture Earth as a single grain of sand. The Milky Way would be a beach and Laniakea an entire coastline stretching beyond the horizon. What defines Laniakea isn't just its size, but the invisible threads that bind it together, rivers of gravity. Every galaxy within it, including ours, is being pulled toward a mysterious focal point called the Great Attractor, a gravitational anomaly hidden behind the dust of our own galaxy's center. Imagine dropping dye into water and watching the currents swirl. That's how galaxies move within Laniakea, flowing along these cosmic tendrils toward a destination we can't yet see. Scientists mapped this motion by observing thousands of galaxies, tracking their subtle redshifts like celestial breadcrumbs leading to the heart of our supercluster. But here's the twist: Laniakea might not even be the final word. Recent studies suggest it could be part of an even larger structure, a filament in the cosmic web connecting to other superclusters. Think of it as a neighborhood in a metropolis we're only beginning to explore. And just like city lights fade into suburbs, Laniakea's edges blur into the voids around it, where galaxies thin out into near nothingness. What's humbling is the scale of our ignorance. The Great Attractor remains poorly understood, obscured by the Milky Way's own bulk. Some theories suggest it's not a single massive object, but a confluence of dark matter and galaxy clusters, a gravitational knot in space-time's fabric. Others propose even larger attractors beyond it, pulling Laniakea itself toward some unseen cosmic destiny. This isn't just about mapping space, it's about time. The light we see from Laniakea's farthest reaches left its source before Earth existed, meaning we're observing a structure as it was when the universe was half its current age. The supercluster has likely shifted, merged, or stretched since then, making our maps more like ancient portraits than current snapshots. Yet even this imperfect view reshapes our place in the cosmos. We're not just residents of the Milky Way, but citizens of Laniakea, swept along in a river of galaxies flowing toward mysteries we've only begun to name. If Laniakea is our galactic neighborhood, then the Pisces-Cetus supercluster complex is the sprawling megacity. It's part of a mind-bending network of superclusters stretching 1 billion light-years from end to end. This isn't just a collection of galaxies, it's a cosmic metropolis, a web of gravitational alliances so vast it redefines our understanding of structure in the universe. Imagine standing in the middle of an endless highway system, where every lane leads to another cluster of galaxies, each one a glittering island in the dark. That's the scale we're dealing with here. What makes this complex so special isn't just its size, but what it reveals about the universe's architecture. Superclusters aren't randomly scattered, they're linked, woven into filaments that trace the backbone of the cosmic web. Pisces-Cetus is like a grand central station in this network, with Laniakea serving as just one of its many districts. Scientists study it like cartographers mapping an uncharted continent, painstakingly measuring galaxy redshifts to reconstruct its three-dimensional shape. The result, a blueprint of gravity's masterpiece, where dark matter's invisible hand has sculpted the largest structures we've ever seen. But here's where things get really strange. For decades, astronomers assumed superclusters were the universe's ultimate organizational tier, that beyond them, matter would disperse evenly. Pisces-Cetus shattered that assumption. Its sheer coherence suggests something deeper, that the cosmos has a fractal-like hierarchy where clusters nest within superclusters, which in turn weave into even larger complexes. It's as if the universe operates on scales we're only beginning to perceive, like ants discovering that their anthill is part of a mountain range. The most tantalizing question Pisces Cetus raises is one of origins. How did gravity assemble something so colossal in the time since the Big Bang? Simulations show that tiny quantum fluctuations in the early universe, smaller than a single atom, could have snowballed into these vast structures over billions of years. But the precision required is staggering. If those initial ripples had been slightly stronger or weaker, the cosmic web might look entirely different, and we might not exist to ponder it. And here's the humbling reality: we're seeing only a snapshot. The light reaching us from Pisces Cetus's farthest reaches is a fossil, a billion-year-old postcard from a younger universe. The complex itself has likely evolved, merged, or stretched in ways we can't yet observe. Yet even this fossilized glimpse challenges our theories, nudging cosmologists to rethink how matter organizes itself across the deepest reaches of space. In the grand tapestry of the cosmos, Pisces Cetus isn't just a thread. It's a reminder that the universe's largest structures are still writing their own epic, and we're only on the first page. Hidden behind the blinding glow of our own galaxy lies a cosmic titan, the South Pole Wall, a curtain of galaxies stretching 1.4 billion light-years across the southern sky. While most colossal structures announce themselves with brilliant clusters, this one remained veiled by the Milky Way's dust and stars, a shadowy giant lurking just beyond our sightline. Astronomers didn't spot it with telescopes but felt it through the subtle tug of its gravity on thousands of galaxies, like sensing a distant storm by the way leaves rustle before the wind arrives. What makes this discovery extraordinary isn't just its scale, but how it defies observation. Imagine trying to map a mountain range while standing in a blizzard. That's the challenge scientists faced, with the Milky Way's dense starfields obscuring nearly a fifth of the sky. Instead of relying on light, researchers analyzed galaxy motions, tracking how entire clusters drift toward the wall's immense gravitational pull. The data revealed a vast sheet of mass, a cosmic continental divide where galaxies pile up like water against a dam. But here's the twist: the South Pole Wall might be even larger than we think. Current maps show it as a crescent-shaped arc, but some simulations suggest it could connect to other superclusters, forming part of a web far grander than our current tools can detect. Its gravitational influence extends so far that galaxies millions of light-years away are caught in its flow, racing toward it at speeds exceeding 600 kilometers per second. That's like watching every city on Earth simultaneously sliding toward a single, invisible magnet. The wall's existence poses a fascinating puzzle. According to standard cosmology, such enormous structures shouldn't form so close to us. The universe is supposed to look roughly uniform in our cosmic neighborhood. Yet here it is, a colossal ripple in space-time just 500 million light-years from Earth. Some theorists speculate it's a fossil from the universe's infancy, a relic of primordial density waves frozen into the fabric of reality. Others wonder if dark energy, the mysterious force accelerating the universe's expansion, played a role in sculpting this behemoth. What's truly humbling is realizing how much we've missed. For decades, this structure lay hidden in plain sight, its presence betrayed only by the silent dance of galaxies. It's a reminder that the cosmos still holds giants lurking in the shadows, their scales so vast we mistake them for the horizon. And just beyond the South Pole Wall, who knows what other structures wait, unseen, rewriting the maps we thought we knew. Most of the universe teems with galaxies, superclusters, and filaments except for the Boots void, a staggering spherical emptiness spanning 330 million light-years where space itself seems to have given up. Picture a bubble so vast that if the Milky Way sat at its center, we wouldn't have known other galaxies existed until the 1960s. Within this cosmic desert, astronomers have found only around 60 galaxies, a number so pitifully small that if the void were a football stadium, those galaxies would be scattered like a handful of grains across the entire field. This isn't just an absence, it's a screaming anomaly, a hole punched through the cosmic web that defies every expectation of how matter should be distributed. How does something this empty even form? The leading theory points to an ancient game of gravitational tug-of-war. Billions of years ago, this region might have been as packed with galaxies as anywhere else, but over eons, the combined gravity of surrounding superclusters could have siphoned away its matter, leaving behind a near vacuum. Imagine pouring water onto a tablecloth. The liquid naturally flows toward the densest folds, leaving dry patches behind. The boot's void might be one of those parched stretches, drained by the cosmic web's insatiable pull. But there's a darker possibility. Some cosmologists suggest voids like boots could be scars from the universe's infancy, where quantum fluctuations in the newborn cosmos left behind regions so underdense that even gravity couldn't gather enough material to form galaxies. If true, this void isn't just an accident, it's a fossil, a preserved imprint of randomness from the first moments after the Big Bang. What's truly unsettling is what the boot's void implies about our theories. The standard model of cosmology predicts some voids, but nothing this colossal. Its existence hints that the universe might be lumpier, more unpredictable than we thought. And if there's one void this size, could there be others, even larger, lurking in the unmapped corners of the cosmos? Yet even in this near-nothingness there's wonder. Those 60-odd galaxies stranded in the void aren't just lonely, they're survivors, clinging to existence in a place where star formation should be nearly impossible. Some glow with unusual intensity, as if screaming across the void, their light a testament to resilience in the face of cosmic indifference. They remind us that even the emptiest places in the universe aren't truly barren, just waiting for us to look closer. Hanging in the cosmic tapestry like a challenge scrawled across the sky, the giant arc defies everything we thought we knew about the universe's structure. This staggering crescent of galaxies spans 3.3 billion light-years, so vast that if you could see it with the naked eye, it would stretch across 35 full moons in our night sky. But its size isn't what's keeping astronomers awake. It's the uncomfortable truth that this colossal formation shouldn't exist. The cosmological principle, one of astronomy's bedrock ideas, states that on the largest scales, the universe should look roughly the same everywhere. No preferred directions, no inexplicable giants lurking in the data. Yet the giant arc laughs in the face of that assumption. Discovered by accident while mapping quasars, this structure isn't a physical chain of galaxies but a statistical ghost, a pattern so coherent that the odds of it forming randomly are less than 1 in 20,000. Imagine shaking a box of glitter and watching it spontaneously arrange itself into a perfect, glowing question mark. That's the level of improbability we're dealing with. Astronomers are torn. Some argue this is just a fluke, a cosmic Rorschach test where our pattern-seeking brains connect dots that aren't truly linked. Others counter that the arc's alignment with other large-scale structures like the Sloan Great Wall suggests something deeper, a hidden architecture woven into the universe's fabric. The debate hinges on a delicate dance of statistics. Are we seeing a real phenomenon, or are we fooled by the same instincts that make us see faces in clouds? What makes the giant arc so tantalizing is its timing. If confirmed, it joins a growing list of anomaly structures like the Hercules-Corona Borealis Great Wall that push against the limits of cosmic evolution. Gravity moves slowly, assembling something this enormous in the universe's 14 billion-year lifespan shouldn't be possible without invoking exotic physics. Some theorists whisper about primordial magnetic fields or dark matter behaving in ways we haven't predicted, while others wonder if we're glimpsing a fingerprint from before the Big Bang itself. For now, the giant arc remains a celestial riddle, its very existence a challenge to our understanding of the cosmos. Whether it's a statistical mirage or a revolutionary discovery, one thing is certain: the universe keeps surprising us, scribbling its secrets in galaxies and daring us to read between the lines. In the early universe's chaotic infancy, when the first galaxies were still flickering to life, something impossible happened. A structure so vast it makes modern superclusters look like pebbles. Meet the huge large quasar group, a staggering chain of 73 quasars stretching 4 billion light-years across the cosmos. To grasp that scale, imagine a bridge so long it would take light, the fastest thing in existence, 40% of the universe's current age, just to traverse it. This isn't just big, it's universe-rewriting big, a formation so colossal that its very existence sends theorists back to their chalkboards. Quasars are the universe's lighthouses, supermassive black holes at the cores of young galaxies, devouring matter so furiously they outshine entire galaxies. Spotting one is rare. Finding 73 aligned in a coherent structure is like discovering a perfectly straight line of volcanoes across a continent. When astronomers first mapped this group, the numbers didn't make sense. According to the cosmological principle, structures larger than 1.2 billion light-years shouldn't exist in the ancient universe. There hadn't been enough time for gravity to sculpt them. Yet here they were, quasars strung across the sky like cosmic pearls, defying every model of how matter organizes itself. So how did this leviathan form? One possibility is dark energy. The mysterious force accelerating the universe's expansion played tricks in the past. If its strength fluctuated, it might have briefly supercharged gravity's pull, allowing matter to clump faster than thought possible. Others speculate these quasars trace the skeleton of a primordial supervoid, a region where dark matter's grip was weak, leaving behind a ghostly imprint. The wildest theory, that we're seeing a collision of universe-sized bubbles from a multiverse, their boundaries etched in quasar light. But here's the twist: the huge large quasar group might not even be a true structure. Some argue it's a chance alignment, quasars unrelated but perfectly positioned to fool us. Yet the odds of that are astronomically low, like rolling a million dice and having them all land on 6. The debate rages, but one thing is certain: if real, this group shatters our understanding of cosmic evolution. Structures this size shouldn't have existed when the universe was barely a third of its current age. It's like finding a skyscraper in the Stone Age, evidence that the cosmos might operate on rules we haven't even imagined. What's haunting is that we're seeing this group as it was 9 billion years ago. By now, its quasars have likely faded, their black holes starving into silence, but their light lingers, a message from a younger, wilder universe that didn't play by the rules we wrote for it. And that's the beauty of astronomy. Every anomaly, every impossible giant, is a clue waiting to rewrite the story we tell about the cosmos. The huge large quasar group isn't just a structure, it's a question mark written in the fire of ancient black holes, daring us to find the answer. The cosmic microwave background, the faint afterglow of the Big Bang, should be as smooth as morning fog, a nearly uniform whisper of heat left over from the universe's fiery birth. But there's a glaring exception, the cold spot, a bizarre one. 8 billion light-year stretch of sky where temperatures plunge like a sudden frost in deep space. This isn't just a minor fluctuation, it's the largest and most puzzling anomaly in the CMB, a cosmic bruise that defies every standard explanation. Some researchers whisper it might be evidence of something far stranger, a collision with another universe, a scar left by a reality beyond our own. At first glance, the cold spot seems like it could be explained by a cosmic void, a vast emptiness where fewer galaxies mean less gravitational pull, cooling photons as they travel through it. But here's the catch: the largest known voids don't come close to the scale needed to create a chill this profound. It's like expecting a gentle breeze to carve out the Grand Canyon. The math simply doesn't add up. When simulations fail, theorists turn to wilder possibilities. One daring idea: this frigid patch is an imprint from a long-ago collision between our universe and a bubble universe, a separate cosmic domain born from the same multiverse foam that birthed our own. The physics is speculative, but the notion is tantalizing. What if the cold spot is the fingerprint of another reality brushing against ours? Yet not everyone buys into the parallel universe theory. Skeptics argue it could be an artifact of incomplete data or an unlucky alignment of smaller voids. Others propose even more exotic explanations, like a tangle in spacetime itself, a cosmic defect left over from the universe's earliest moments. The truth is, we're still peering through a keyhole, trying to interpret shadows on a wall we can't fully see. What makes the cold spot so compelling isn't just its mystery, but what it represents: a crack in our understanding, a reminder that the universe might be far weirder than we've dared to imagine. Whether it's proof of a multiverse or just an unexplained statistical fluke, this icy anomaly challenges us to rethink the boundaries of reality. And until we crack its secrets, it lingers like a cosmic question mark, waiting for the next bold mind to finally decipher its meaning. In the grand dance of galaxies, everything should move randomly, like fireflies in a summer field, each cluster drifting on its own path, pulled only by the gravity of nearby matter. But the universe loves to break the rules. Astronomers have discovered something eerie. Hundreds of galaxy clusters are all streaming in the same direction at nearly 1,000 kilometers per second, as if dragged by an invisible current. They call it the dark flow, and its existence hints at forces at work beyond the edges of everything we can see. This isn't just a subtle drift, it's a cosmic river with entire superclusters caught in its pull. Imagine standing on a beach where every wave, no matter how far apart, rolls toward some unseen point beyond the horizon. That's what's happening here, but on a scale so vast it defies explanation. The strangest part: the direction of this flow can't be explained by anything in the observable universe. No known supercluster, no immense void, not even the Shapley attractor, a colossal concentration of mass billions of light-years away, can account for this motion. It's as if something outside our cosmic horizon is tugging at the fabric of space itself. Naturally, not everyone accepts this idea. Skeptics argue it might be a measurement error, a distortion caused by incomplete data or overlooked local forces. But the evidence is persistent. Multiple studies, including analyzers of the cosmic microwave background, have detected this mysterious drift. If real, the implications are staggering. One radical theory suggests the dark flow could be the gravitational fingerprint of another universe, a neighbor in the multiverse brushing against our own, its mass warping our space-time from beyond the veil. Others propose it's a relic from the instant after the Big Bang, when the newborn universe's expansion left behind imprints we're only now beginning to sense. Here's what keeps scientists up at night. If the dark flow is real, it means our universe isn't as self-contained as we thought. There's something out there beyond the cosmic horizon, massive enough to bend the paths of galaxies like a magnet tugging at iron filings. We can't see it, we can't directly measure it, but its influence ripples through the darkness, a silent reminder that the cosmos still holds mysteries too vast for our telescopes to capture. The dark flow doesn't just challenge our maps of the universe, it questions the very boundaries of reality. Are we part of something even grander, a tapestry of universes whose gravity spills over into ours? Or is this some fundamental flaw in our understanding of physics, waiting to rewrite the textbooks? For now, all we know is that the galaxies are moving, and whatever's pulling them lies in the shadows just beyond our grasp. We often picture the Milky Way drifting through a universe speckled with galaxies, floating in a vast cosmic sea. But what if our entire galactic neighborhood is actually sitting inside a bubble, a staggering void where matter is strangely scarce? Meet the KBC void, a 2 billion light-year-wide underdense region that makes our local universe feel like a desert island in an ocean of nothingness. This isn't just any void, it's the largest known cosmic emptiness ever discovered relative to its location, and guess what? We're right at its heart. The KBC void, named after astronomers Keenan, Barger, and Cowie, explains one of cosmology's nagging mysteries: why different measurements of the Hubble constant, the rate of the universe's expansion, keep disagreeing. Here's the twist: when you're inside a void, space doesn't behave the way it does outside. Gravity's grip weakens where matter is sparse, so the space within the void expands faster than denser regions beyond it. Imagine blowing up a balloon with a thin patch. The thin part stretches more easily, distorting the whole shape. That's our reality. We're in that thin patch, watching galaxies outside the void race away faster than our local measurements predict. But how does a void this colossal even form? One theory suggests it's a fossil from the universe's earliest moments, a primordial fluctuation that never quite filled in. Another proposes it's the result of smaller voids merging over billions of years, like soap bubbles combining into one giant vacancy. What's eerie is the scale. If the KBC void were a sphere, its surface would be lined with superclusters, their gravity tugging inward while dark energy pushes outward, creating a tug of war that stretches space itself. The irony is exquisite. For centuries, we assumed we occupied no special place in the cosmos, yet here we are, nestled in a bubble so vast it skews our perception of the entire universe. Those discrepancies in the Hubble constant, they might not be errors at all, but clues, telling us we're floating in a pocket of emptiness so immense it bends the rules. And if that's true, it means our cosmic address isn't just another suburb in the universe, it's a quiet corner of a cavern so large, we're only now beginning to grasp its walls. What's haunting is how much this void hides. Light from galaxies beyond it passes through this underdense region, subtly dimming like headlights fading in fog. Astronomers call this the void lensing effect, and it's another reason the KBC void warps our cosmic perspective. We're not just in the void, we're seeing the universe through it, like looking through a funhouse mirror that stretches reality itself. The KBC void forces us to confront a humbling possibility: that even our most precise measurements might be colored by our place in space. It's a reminder that the universe doesn't owe us clarity. Sometimes it wraps its secrets in emptiness, leaving us to piece together the truth from shadows and echoes. And if we're truly adrift in this bubble, who knows what other illusions of scale and distance we've yet to uncover? Most cosmic giants hide their enormity behind the quiet drift of galaxies, but Alcyonius roars across the cosmos, a radio galaxy so vast its twin jets stretch 16.3 million light-years from tip to tip. That's 160 times the diameter of our Milky Way, making it the largest known structure ever carved out by a single supermassive black hole's tantrum. Picture a black hole at the galaxy's core, gorging itself on gas and dust until it vomits twin beams of plasma at nearly light speed, punching through intergalactic space like a celestial blowtorch. These jets don't just fade, they burrow outward for millions of years, inflating gargantuan lobes of radio-emitting gas that glow across the electromagnetic spectrum. What makes Alcyonius so baffling isn't just its size, but its quiet power. Most radio galaxies with jets this colossal come from monstrous black holes in dense galaxy clusters where abundant fuel feeds their outbursts. Yet Alcyonius lives in a cosmic backwater, its host galaxy unremarkable, its black hole no heavier than others we've seen. It's like discovering a gentle breeze somehow carved the Grand Canyon. Scientists are scrambling to explain how this unassuming beast produced such titanic structures. Could its environment, a sparse intergalactic medium, allow its jets to expand unchecked, like flames spreading through dry grass? Or does its black hole have a hidden trick, some unknown spin or magnetic field configuration that supercharges its eruptions? The discovery shakes our understanding of galactic evolution. If something this enormous can emerge from such humble beginnings, what else have we underestimated? Alcyoneus might not be unique, just the first of its kind we've spotted. Its radio glow visible thanks to a fortunate alignment. There could be larger giants lurking undetected, their jets stretching even farther into the void. But here's the twist: we're seeing Alcyoneus as it was 3 billion years ago. By now, those colossal jets may have dissipated, their energy fading into the cosmic background. Or perhaps they've grown larger still, weaving through the cosmic web like invisible highways. Either way, this Leviathan reminds us that the universe loves extremes, and that even the quietest black holes can rewrite the rules when we're not looking. Hidden in the depths of our cosmic backyard lies Saraswati, a supercluster so massive it bends the very fabric of space around it. Named after the ancient Hindu goddess of wisdom and rivers, this 600 million light-year-wide behemoth flows across the universe like a celestial Ganges, carrying 43 galaxy clusters in its gravitational current. Together, they weigh 20 quadrillion times the mass of our Sun, a number so large it loses all meaning. If each star in Saraswati were a grain of sand, you'd need every beach on Earth just to hold a fraction of them. What makes Saraswati extraordinary isn't just its size but its age. Most superclusters we've found are relatively young, still gathering mass like cosmic teenagers. Saraswati, though, is a relic, a fully matured structure that formed when the universe was barely half its current age. That's like finding a skyscraper in the middle of the Stone Age. It shouldn't exist according to our models of cosmic evolution. Gravity needs time to weave galaxies into clusters and clusters into superclusters, yet here's Saraswati, standing tall in the universe's adolescence as if it cheated time itself. Peering into this supercluster is like opening a window to the past. The light we see from its farthest galaxies began its journey when the universe was just 10 billion years old, meaning we're witnessing Saraswati in its prime. But here's the haunting part. By now, this colossal structure has likely grown even larger, merging with neighboring superclusters in a dance that's been ongoing for eons. We're seeing only a snapshot, a single frame in a movie that's still playing. The discovery of Saraswati forces astronomers to confront a glaring question. How did something this vast and dense form so early? One theory points to dark matter, the invisible scaffolding of the cosmos, clumping faster than expected in certain regions, creating gravitational wells deep enough to trap galaxies at breakneck speed. Another possibility is that Saraswati sits at a cosmic crossroads, where filaments of the web intersect, funneling galaxies together like rivers merging into a delta. Yet Saraswati's true significance might lie in what it reveals about our place in the universe. From our tiny vantage point, it's easy to assume we're somewhere ordinary, but the presence of such an ancient giant so close by hints that we might be floating in a far richer, more interconnected cosmic neighborhood than we ever imagined. It's a humbling reminder that the universe has been building grandeur on scales we're only beginning to measure, and Saraswati is just one thread in a tapestry still being woven. If the universe has a symphony, the Horologium Reticulum supercluster is one of its most dramatic movements, a sprawling composition of light and shadow stretching 550 million light-years across the southern sky. Unlike uniform superclusters, this titan thrives on contrast, flipping between extremes like a cosmic seesaw. On one end, galaxies packed together so tightly they practically overlap, their gravity warping space into funhouse mirrors. Just a few million light-years away, voids gape like black holes, regions so empty they make the Boots void look crowded. It's as if the universe took a brush and painted with pure light here, pure darkness there, leaving no middle ground. What creates such stark divides? The answer lies in an ancient gravitational tug-of-war. Billions of years ago, dark matter, the invisible glue of the cosmos, clumped unevenly across this region. Where it pooled thickly, galaxies swarmed like moths to a flame. Where it thinned, matter evaporated, drained away by the pull of neighboring structures. The result is a fragmented empire, its borders etched by forces we can't even see. Astronomers call it a multifractal system where density swings wildly at every scale. Zoom in on a cluster and you'll find subclusters with their own empty pockets. Zoom out and the entire supercluster seems to pulse between congestion and desolation. One of its crown jewels is the Horologium cluster, a gleaming metropolis of galaxies weighing in at 2 quadrillion solar masses. Here, thousands of galaxies orbit a common center, their paths twisted by dark matter's grip. Yet venture just 30 million light-years east and you'll hit the reticulum void, a bubble so devoid of matter that telescopes catch only a handful of lone galaxies, drifting like shipwrecks in an ocean of nothingness. This yin-yang structure isn't just beautiful, it's a time capsule. The supercluster's light reaches us from an era when the universe was 3/4 its current age, meaning we're glimpsing a snapshot of adolescence frozen in starlight. But Horologium Reticulum's real magic lies in what it reveals about cosmic evolution. Most models predict matter should smooth out over vast distances, yet here we see wild imbalances persisting across 500 million light-years. Some theorists argue it's evidence of Baryon acoustic oscillations, sound waves from the Big Bang that stamped permanent ripples into matter's distribution. Others suspect the supercluster might be a node in the cosmic web, a place where multiple filaments intersect, funneling galaxies into dense knots while leaving gaps between them. The most humbling thought, this supercluster is moving. Every galaxy within it is being tugged toward the Shapley supercluster, the largest gravitationally bound structure we've ever mapped. Horologium Reticulum isn't just a static monument, it's a traveler, swept along in a current we're only beginning to chart. And as it drifts, it stretches, its voids growing emptier, its clusters denser, etching its story deeper into the fabric of space. For astronomers, it's a living laboratory, a place where the universe's two most powerful forces, gravity and emptiness, play out their endless duel on a stage so vast we're still learning how to read the script. When astronomers first detected the cold spot in the cosmic microwave background, they assumed it had to be a fluke, a statistical glitch in the data. But then they found the Eridanus supervoid, a staggering emptiness spanning 1.8 billion light-years, positioned right where the universe's temperature takes that mysterious plunge. The coincidence seemed too perfect, a cosmic refrigerator sitting exactly where the background radiation is coldest. Could this void be the culprit, its lack of galaxies and matter-chilling photons as they travel through it? Or is this just an illusion, a chance alignment that's fooling us into seeing connections where none exist? The physics seems straightforward at first glance. When light passes through a void, it loses energy climbing out of the gravitational well, a process called the integrated Sachs-Wolf effect. Think of it like rolling a ball up a hill. It slows down as it fights gravity. In a void where matter is scarce, there's less gravity to pull photons back, so they emerge slightly cooler, like a traveler stepping out of a warm valley into thin mountain air. The Eridanus supervoid is vast enough that this cooling effect should be noticeable, potentially explaining the cold spot's frigid temperatures. But here's the problem. Simulations show even a void this enormous shouldn't create a chill this profound. The math leaves a gap, like trying to explain an ice age with just a light breeze. Some researchers argue the supervoid might only account for a fraction of the temperature drop, leaving the rest a mystery. Others go further, suggesting the void and the cold spot might not be connected at all, that we're seeing two rare cosmic anomalies that just happen to overlap from our viewpoint. Then there's the timing puzzle. The Eridanus supervoid is relatively close, cosmically speaking just 3 billion light-years away. The cold spot, however, is imprinted on the cosmic microwave background, which comes from 13.8 billion years ago. How could a structure so much younger leave a mark on the universe's oldest light? One radical idea proposes that the void isn't just a hole. It's a fossil, a remnant of some primordial density fluctuation that shaped both the early universe and the later distribution of galaxies. What makes this debate so captivating is what's at stake. If the void truly caused the cold spot, it would mean we've found a rare cosmic lab to study how large-scale structures affect the fabric of space-time. But if it's just a coincidence, the cold spot becomes even stranger, a mystery with no clear explanation beyond the edge of our current physics. Either way, this pair, the void and the spot, stands as a reminder that the universe loves to blur the line between pattern and accident, leaving us to untangle the difference. The Boss Great Wall doesn't just break records, it shatters our assumptions about how the universe organizes itself. Stretching a staggering 1 billion light-years across the cosmos, this galactic leviathan isn't a random scattering of stars but a carefully mapped filament, a thread in the cosmic web so vast it could connect thousands of Milky Ways end to end. What makes this structure extraordinary isn't just its scale, but how we found it, not by spotting glowing galaxies, but by listening to the echoes of the Big Bang itself. Scientists discovered the Boss Great Wall using a technique called Baryon acoustic oscillation, or BAO, a fancy term for measuring the faint ripples frozen into the universe's matter when it was just 400,000 years old. Picture dropping a stone into a pond and watching the ripples spread. Now imagine that pond is the entire observable universe, and those ripples are barely perceptible density variations that eventually grew into galaxies. By mapping how galaxies cluster at specific intervals roughly 500 million light-years apart, astronomers traced the outline of this titanic wall, revealing a structure so immense it rivals the Sloan Great Wall in scale. But here's where it gets even more fascinating. The Boss Wall isn't just a relic of the past, it's a key to unlocking one of cosmology's greatest mysteries, dark energy. The spacing between galaxies in this structure acts like a cosmic ruler, letting scientists measure how fast the universe has expanded over time, and the measurements don't match expectations. The wall's sheer size and the distribution of its galaxies suggest dark energy. The mysterious force accelerating the universe's expansion might be stronger or weirder than we thought. Some theories even speculate that this wall's peculiar shape could hint at dark energy's evolution, as if the universe's expansion left fingerprints in the way galaxies clumped together. What's humbling is that we're seeing this wall as it was 7 billion years ago, a snapshot frozen in light. By now, its galaxies may have drifted apart, pulled by the relentless stretch of dark energy, or merged into even larger clusters. Yet, even as a fossil, the Boss Great Wall forces us to rethink the cosmos. It's not just a structure, it's a time capsule, a measuring stick, and a puzzle all at once, reminding us that the universe writes its secrets in galaxies, and we're only just learning to read the language. Tucked away behind the Milky Way's glittering veil lies a cosmic giant we almost missed, the Vela supercluster, a sprawling metropolis of galaxies spanning 300 million light-years. For decades, this titanic structure hid in plain sight, camouflaged by the dense starlight and dust of our own galaxy's plane. It's like trying to spot a mountain range through a blizzard. The very richness of our celestial neighborhood blinded us to the colossal neighbor next door. Only in 2016 did astronomers piece together its existence, using radio telescopes to peer through the galactic glare and uncover a web of galaxies so vast it reshapes our local cosmic map. What makes Vela extraordinary isn't just its size, but its defiance of expectations. Most superclusters this massive lie billions of light-years away, relics of a younger universe. But Vela is practically next door, just 800 million light-years distant, a reminder that the cosmos still harbors giants in its backyard. Its galaxies move in eerie synchrony, pulled by the supercluster's combined gravity like leaves caught in a river's current. Mapping their motions revealed something even stranger. Vela might be merging with our own Laniakea supercluster, a slow-motion collision of cosmic continents that will stretch over eons. The discovery cracks open a puzzle. How did something this massive form so close to us without us noticing? The answer lies in a cosmic blind spot. the zone of avoidance, a region of the sky where the Milky Way's bulk blocks our view. Traditional telescopes see only haze here, but radio waves slip through, carrying whispers from galaxies beyond. By stitching together data from surveys like Parkes and Mercator, astronomers spotted the telltale clumping of galaxies, their redshifts tracing the outline of a supercluster lurking in the shadows. But Vela's secrets go deeper. Its galaxies are older and quieter than those in younger superclusters, as if the structure hit the pause button on star formation long ago. Some researchers speculate it's a fossil, a relic from an era when the universe was denser, its galaxies crammed together before dark energy began stretching space apart. Others see it as evidence of a hidden dynamic, that superclusters aren't just passive scaffolds but active players, their gravity shaping the fate of galaxies within them over billions of years. The most tantalizing thought, Vela might not be alone. If one supercluster could hide behind the Milky Way, others could too, silent giants waiting to rewrite our understanding of the cosmic web. For now, Vela stands as a testament to both the universe's grandeur and our own myopia, a reminder that sometimes the biggest discoveries aren't at the edge of the known, but just beyond the edge of what we've thought to look for. At the edge of our observable universe, where light takes nearly 11 billion years to reach us, floats a cosmic blueprint Hyperion, the most massive and earliest proto-supercluster ever discovered. Unlike the polished superclusters of today, this colossal structure is a snapshot of raw construction, a bustling cosmic workshop where gravity is still assembling the pieces. Picture a city skyline mid-construction with cranes hovering over half-built towers, except here, the towers are galaxies and the cranes are the invisible hands of dark matter and gravity, shaping the universe's largest structures in their infancy. Hyperion's staggering scale defies intuition. Spanning over 300 million light-years and weighing in at 5 million billion times the mass of our Sun, it's a Frankenstein's monster of galaxy clusters, each one a glowing suburb in this sprawling cosmic metropolis. But what truly astonishes astronomers isn't just its size, it's its age. Hyperion existed when the universe was less than 3 billion years old, a cosmic toddler by universal standards. According to conventional models, structures this enormous shouldn't have had time to form so soon after the Big Bang. It's like finding a fully grown redwood in a garden where only saplings should exist. The secret to Hyperion's precocious growth might lie in its peculiar anatomy. While modern superclusters like Laniakea are organized into neat filaments, Hyperion is chaotic, a tangle of galaxy clusters smashed together in a gravitational free-for-all. Instead of the elegant cosmic web we see today, it resembles a knotted ball of yarn with matter clumping in ways that challenge our simulations. Some scientists compare it to an overeager artist splashing paint onto a canvas, creating dense splotches before stepping back to refine the details. Peering into Hyperion is like rewinding a time-lapse of urban development. Its galaxies are younger, hotter, and bursting with star formation, their skies ablaze with the light of newborn stars. Unlike the sedate, aging galaxies in modern superclusters, these are cosmic teenagers, reckless, bright, and brimming with energy. But the real treasure lies in the spaces between them, vast reservoirs of gas, the raw material for future stars, swirling in gravitational eddies that will one day solidify into the supercluster's backbone. Yet for all its chaos, Hyperion holds clues to one of cosmology's biggest mysteries: how dark matter orchestrated the universe's large-scale structure. Its uneven distribution suggests that dark matter didn't clump uniformly in the early universe. Instead, it pooled in dense pockets, creating gravitational wells deep enough to trap entire galaxy clusters before the cosmos had even settled into its current rhythm. If confirmed, this could mean our models need recalibrating, accounting for a universe where structure formed faster, messier, and more unpredictably than we ever imagined. The most humbling thought: Hyperion is long gone. The light we see today shows it as it was 11 billion years ago. By now, its galaxies have likely merged, cooled, or drifted apart, their stories lost to time. But in its fleeting youth, this proto-supercluster left behind a message, a reminder that the universe's grandest designs were born not in perfection, but in glorious, untamed chaos. And somewhere out there, beyond the limits of our telescopes, other Hyperions may be taking shape, rewriting the rules of cosmic architecture all over again. The universe loves to weave threads of galaxies into patterns, and the Coma Wall is one of its finest tapestries, a 500 million light-year filament stitching together two of the cosmos' most bustling hubs, the Coma and Leo clusters. Picture a highway of stars, gas, and dark matter arcing through the void, a bridge so vast it would take light, the fastest traveler we know, 500 million years just to cross it. This isn't just a string of galaxies, it's a lifeline, a gravitational umbilical cord feeding matter into the clusters it connects, shaping their growth across cosmic time. What makes the Coma Wall so special is its role as a cosmic delivery system. Galaxies along its length don't just sit idle, they're in motion, streaming toward the clusters at either end like commuters drawn to a city's bright lights. The Coma cluster, one of the densest gatherings of galaxies we've found, anchors one end, its 1,000+ members swirling in a gravitational dance. At the other end, the Leo cluster hums with its own symphony of stars. Between them, the wall acts as a funnel, channeling galaxies into these celestial metropolises over billions of years. But here's the twist: the Coma Wall isn't unique. It's a textbook example of the cosmic web's finer strands, the smaller-scale filaments that crisscross the universe like capillaries in a living organism. While titans like the Hercules-Corona Borealis Great Wall dominate headlines, structures like this reveal the day-to-day mechanics of cosmic evolution. They're the quiet laborers of the universe, the unseen scaffolding that builds the grand clusters we marvel at. Mapping the wall wasn't easy. Unlike glowing superclusters, filaments are faint, their galaxies scattered like distant lanterns along a dark road. Astronomers had to piece together its structure by measuring redshifts, the stretching of light as galaxies move away from us, to reconstruct their positions in three-dimensional space. The result, a blueprint of gravity's handiwork, showing how even the smaller structures in the cosmos operate on scales beyond human intuition. Yet the Coma Wall offers more than just a lesson in scale. It's a time machine. The light we see from its farthest reaches left when the universe was younger, meaning we're watching the filament as it was billions of years ago. By comparing it to newer structures, scientists can trace how filaments evolve, whether they thicken with time, fade, or collapse into clusters. It's like comparing a sapling to a mature tree, studying the growth rings of cosmic history. And then there's the dark matter factor. The wall's galaxies are just the visible icing on an invisible cake. Most of its mass is dark matter, the mysterious substance that sculpts the cosmic web's contours. Without it, the Coma Wall would never have held together. Its galaxies would have drifted apart like smoke in the wind. Instead, they cling to this dark backbone, riding its gravitational currents toward an inevitable collision with the clusters at either end. The humbling truth: we're witnessing a fleeting moment. In another few billion years, the Coma Wall may be gone, its galaxies absorbed into the clusters, its structure dissolved by the relentless pull of gravity. But for now, it stands as a reminder that even the small structures of the cosmos are anything but insignificant. They're the threads stitching the universe together, one galactic filament at a time. Before the Sloan Great Wall, before the Hercules-Corona Borealis structure rewrote the rulebook, there was the CFA2 Great Wall, a 500 million light-year-long parade of galaxies that shook astronomy to its core. Discovered in 1989 by a team at the Harvard-Smithsonian Center for Astrophysics, this titanic ribbon of galaxies didn't just break records, it shattered the way we thought the universe was organized. Up until then, scientists assumed matter was spread relatively evenly across the cosmos, with galaxies scattered like sand on a beach. The CFA2 wall proved them wrong, revealing that the universe prefers to build on scales so vast they defy human intuition. Mapping this structure was like trying to sketch a mountain range while standing at its base. Astronomers used redshift surveys measuring how light from galaxies stretches as they move away from us, to reconstruct their positions in three-dimensional space. The result was a revelation. Galaxies weren't randomly sprinkled through space but clung to an immense thread-like structure, a cosmic spine stretching across the void. Suddenly, the universe had anatomy, a skeleton of galaxies woven into patterns we'd never dared to imagine. What made the CFA2 wall so revolutionary wasn't just its size but its implications. If structures this colossal existed, then our understanding of gravity, dark matter, and cosmic evolution had gaping holes. Standard models struggled to explain how gravity could sculpt something so vast in the time since the Big Bang. Some theorists scrambled to adjust their equations, while others wondered if dark matter, the invisible glue holding galaxies together, behaved in ways we hadn't predicted. The wall became a living laboratory, a testing ground for ideas that would reshape cosmology for decades to come. Yet for all its grandeur, the CFA2 wall is a lesson in humility. Compared to later discoveries like the Sloan Great Wall or the Hercules-Corona Borealis structure, it's almost modest. But that's the irony of progress. Every giant we find makes the last one seem smaller. What hasn't faded is its legacy. This was the first crack in the cosmological principle, the first hard evidence that the universe isn't just a uniform expanse but a tapestry of structures so immense they redefine the word large. Today, the CFA2 wall feels like an old pioneer, the discovery that taught us where to look. Without it, we might never have thought to search for even greater giants, never have realized how much we'd underestimated the universe's appetite for scale. It's a reminder that every cosmic record is temporary, that every time we think we've found the edge of what's possible, the universe laughs and shows us something larger. Just a cosmic stone's throw away from our own Milky Way, the sculptor wall quietly looms, a 400 million light-year curtain of galaxies so close we could almost reach out and touch it. Unlike the Hercules-Corona Borealis Great Wall or the Sloan Great Wall, which sit billions of light-years distant, this structure is practically in our backyard, a mere 600 million light-years from Earth. But here's the irony, its proximity doesn't make it easy to study. In fact, the sculptor wall embodies the paradox of cosmic observation. Sometimes, the closer something is, the harder it is to see the full picture. Picture trying to sketch a mountain range while standing at its base. That's the challenge astronomers face with the sculptor wall. Because it sprawls across such a wide swath of our nearby universe, its sheer scale overwhelms our field of view. Distant walls, seen edge-on, appear as thin, crisp lines in redshift surveys. But the sculptor wall wraps around us, its galaxies spread across such a vast volume that mapping its full extent is like trying to trace the outline of a continent from a single street corner. It's not dim, it's too big to fit into our cosmic frame, yet this wall offers something rare, a close-up look at the cosmic web's architecture. While titans like the Boss Great Wall or the CFA2 wall are fossils, their light reaching us from billions of years ago, the sculptor wall is a living, breathing structure. Its galaxies are still evolving, still falling into its gravitational embrace, giving us a front-row seat to how filaments shape galactic destiny. The Coma cluster might be where galaxies go to retire, but the sculptor wall is where their midlife drama unfolds, collisions, mergers, and slow dances dictated by dark matter's invisible hand. What's fascinating is how differently light behaves here. When we observe distant walls, their light is redshifted, stretched by the expansion of the universe into the infrared. But the sculptor wall's light arrives almost pristine, barely touched by cosmic time. That means we see its galaxies in their full glory, their colors vibrant, their shapes sharp. no need for the correction factors astronomers apply to faraway structures. It's like comparing a faded Polaroid of your grandparents to a high-resolution photo of your next-door neighbor. The difference in clarity is staggering. But the sculptor wall's greatest gift might be its humility. It's not the biggest, not the farthest, not the most massive, yet it teaches us that scale isn't everything. Sometimes the most valuable discoveries aren't the record breakers, but the ones that let us study the universe's mechanics up close. In its unassuming way, this wall reminds us that the cosmos doesn't just operate on extremes. It's also in the quiet, nearby details, waiting for us to look closer. Deep in the heart of the Ophiuchus supercluster, roughly 390 million light-years from Earth, a sleeping giant once woke infuriated, carving a 15 million light-year wide crater into the fabric of space itself. This isn't just any explosion. It's the largest cosmic detonation we've ever witnessed, dwarfing every supernova, gamma-ray burst, and galaxy collision in recorded history. 5 times more energetic than the previous record holder, this eruption didn't just ripple through space, it rewired it, leaving behind a scar so vast you could fit 15 Milky Way galaxies end to end inside it. And the culprit, a supermassive black hole with a temper tantrum for the ages. How does a black hole, an object known for sucking matter in, blow a hole in the universe? The answer lies in a paradox. Even black holes have limits. At the center of the Ophiuchus galaxy cluster, a black hole weighing billions of suns gorged itself on gas and dust until it couldn't swallow another bite. Instead of quietly digesting, it belched out a jet of plasma at nearly light speed, a beam so intense it punched through the cluster's hot gas like a cosmic blowtorch. But here's the twist: the jet didn't just dissipate. It stalled, then detonated outward in a shockwave so powerful it blasted a cavity into the surrounding medium, a cosmic air bubble in a sea of superheated gas. The scale of this explosion is hard to fathom. The energy released 580 million times the energy of the Sun per second, sustained for tens of millions of years. That's enough power to boil away every ocean on every planet in the Milky Way a trillion times over. Yet for decades we missed it entirely. Unlike a supernova's flashy finale, this explosion unfolded in slow motion, detectable not by light but by the ghostly imprint it left on the supercluster's X-ray glow. Only when astronomers combined data from radio telescopes and space-based X-ray observatories did the truth emerge. We'd found the universe's largest known explosion since the Big Bang, hiding in plain sight. What makes this discovery so thrilling isn't just the spectacle, it's the implications. Black holes aren't just destroyers, they're architects, shaping the evolution of galaxy clusters by heating and redistributing matter on scales we once thought impossible. The Ophiuchus eruption is a fossilized lesson in extremes, proving that even the universe's most voracious monsters have limits, and when they hit them, the results rewrite the rules of physics. Yet the most haunting question remains: if we missed this cataclysm for so long, what other titanic explosions might be lurking in the archives of our telescopes, waiting for us to piece together their stories? The universe, it seems, still holds fireworks grand enough to humble even our boldest imaginations. Buried in the deep time archives of the cosmos, the Lynx supercluster stands as a cosmic fossil, a sprawling megastructure so distant its light takes 10 billion years to reach us, showing us the universe as it was when galaxies were still learning how to cluster. While modern superclusters like Laniakea resemble elegant spiderwebs, Lynx is a chaotic toddler, its galaxies smashing together in a gravitational mosh pit with none of the orderly filaments we see today. This isn't just a supercluster, it's a time capsule preserving the messy adolescence of cosmic structure formation. What makes Lynx so fascinating is its sheer improbability. At this early epoch, the universe was only a quarter of its current age, far too young, according to most models, for gravity to have assembled something so colossal. Yet there it is, a 500 million light-year-wide sprawl of galaxies weighing in at a staggering 100 quadrillion solar masses. It's like finding a fully formed city in the middle of the Stone Age, challenging everything we thought we knew about how quickly cosmic architecture emerges. The key to Lynx's precocious growth might lie in its environment. While today's superclusters form where dark matter filaments intersect, Lynx seems to have grown from a primordial overdensity, a lucky region where matter pooled extra thickly in the aftermath of the Big Bang. Picture a pot of boiling water. Most bubbles are small, but occasionally a few merge into a giant froth. Lynx could be that cosmic froth, a rare pocket where gravity hit the cosmic accelerator, cramming galaxies together at breakneck speed. But here's where it gets even stranger. Unlike modern superclusters where galaxies orbit in stately spirals, Lynx's members are frenetic, blazing with star formation and colliding at dizzying rates. Their light is tinged blue, the signature of young, hot stars, unlike the reddish glow of aging galaxies in nearby clusters. This isn't a retirement community, it's a galactic nursery, bursting with the raw energy of a universe still figuring itself out. Mapping Lynx required a cosmic detective story. Astronomers didn't just point telescopes and snap a photo, they pieced together its existence by analyzing thousands of faint galaxy redshifts, like reconstructing a city's skyline from scattered postcards. The result revealed a structure so vast it shouldn't exist yet, forcing theorists to revisit their simulations. Some now suggest dark matter might have clumped faster in the early universe, or that mysterious forces like primordial magnetic fields gave structure formation a head start. Yet the most humbling realization, we're seeing Lynx in its infancy. By now, those frenzied galaxies have likely merged, cooled, or been ripped apart by dark energy's expansion. What remains might be the skeleton of a modern supercluster, its youthful chaos long settled into the cosmic web's stately order. Lynx isn't just a relic, it's a Rosetta Stone, helping us decode how the universe grew from primordial soup to the structured vastness we see today. And somewhere out there, beyond the reach of our telescopes, other Lynx-like giants may be taking shape, rewriting the rules of cosmic evolution all over again. While most of the cosmos dazzles with galaxies and superclusters, the microscopium void sits like a gaping hole in the celestial fabric, a 300 million light-year-wide emptiness lurking just beyond our local void. Picture throwing a stone into a pond, only for it to vanish without a single ripple. That's the eerie stillness of this void, where galaxies are so sparse you could fly for hundreds of millions of light years and see nothing but darkness. But don't let the emptiness fool you. This void isn't just a barren wasteland. It's a cosmic puppeteer, quietly tugging at the motion of galaxies around it with gravitational strings we're only beginning to trace. What makes the microscopium void so intriguing isn't just its scale. It's the way it bends the rules of galactic traffic. Normally, galaxies move in predictable orbits, bound by the gravity of nearby clusters. But here, the void's sheer lack of mass creates a gravitational repellent, pushing galaxies away like a cosmic vacuum cleaner running in reverse. Nearby galaxy clusters, including our own local group, feel this subtle tug, their paths skewed as if space itself were tilting beneath them. Scientists call this void inertia, a phenomenon where emptiness behaves like a force, sculpting the flow of matter on scales we once thought were too vast to be affected. The irony, we almost missed it entirely. Unlike glittering superclusters, voids don't announce themselves with light. Astronomers mapped microscopium by studying what wasn't there, painstakingly charting galaxy densities until the void's outline emerged like a shadow in negative space. The deeper they looked, the stranger it got. Some galaxies at the void's edges orbit nothing at all, their trajectories looping around an invisible center of nothingness as if held by a ghost's hand. It's a reminder that in the cosmic web, emptiness can shape the universe as powerfully as matter. Yet the microscopium void holds a darker secret. It might be growing. Voids expand faster than the universe itself, their edges stretching under the push of dark energy. Over billions of years, this void could swallow more galaxies, thinning out the cosmic neighborhood until even the nearest clusters are isolated islands in an ever-widening sea of nothing. But here's the twist: this expansion isn't just destruction, it's a rebirth. As voids grow, they squeeze matter into the filaments between them, fueling the birth of new superclusters. The very emptiness that devours galaxies today might sow the seeds for tomorrow's colossal structures. So while we marvel at the universe's glittering cities of stars, let's not forget the silent architects, the voids. They're not just empty spaces, they're the cosmic counterbalance, the yin to matter's yang. And in their vast, motionless depths, they hold clues to the universe's most elusive question: how nothingness shapes everything. Hovering in the southern sky like a cosmic signature, the Groove's wall spins a mystery, an 800 million light-year filament of galaxies moving in eerie unison, as if tugged by unseen hands. Unlike most large-scale structures that drift lazily with the universe's expansion, this southern hemisphere giant has a peculiar velocity, a bulk flow so pronounced it hints at something monumental lurking beyond our current maps of the cosmos. Imagine standing on a raft, feeling the current pull you toward an invisible waterfall just beyond the horizon. That's the unsettling sensation astronomers get when studying this wall's motion, an unexplained drift that defies the predictable tug of nearby superclusters. What makes the Groove's wall so fascinating isn't just its scale but its defiance. Galaxies within it stream toward a common point at nearly 300 kilometers per second, a motion too coordinated to be explained by visible matter alone. The usual suspects nearby superclusters like Shapley or the Vela supercluster can't account for this collective movement. It's as if the wall is caught in the gravitational undertow of something even more massive, something so vast it lies beyond the edges of our observable universe. Scientists call this phenomenon dark flow, a controversial idea suggesting that structures outside our cosmic horizon might be exerting a pull on the matter we can see. Mapping this motion required a cosmic detective's patience. Astronomers measured redshifts across thousands of galaxies in the wall, not just to plot their positions but to clock their velocities. The data revealed a startling pattern. Galaxies weren't just receding uniformly with the universe's expansion, they were skewing sideways like leaves swept by a hidden current. Some researchers argue this could be evidence of a supercluster, a concentration of mass so colossal it bends space-time like a bowling ball on a trampoline, warping the paths of galaxies millions of light-years away. Others propose even wilder theories, like the gravitational imprint of a sibling universe brushing against our own in the multiverse foam. Yet the Groove's wall's mystery deepens when you consider its timing. The light we see from its farthest reaches is ancient, emitted when the universe was half its current age. By now, its galaxies may have been swallowed by larger structures or scattered by dark energies' push. But their motion, etched into the light we observe, remains a fossilized clue, a snapshot of forces we're only beginning to fathom. It's a reminder that the universe's largest structures aren't just scenery, they're actors in a gravitational drama where the script is still being written. What's humbling is how much we still don't see. If the Groove's wall's motion truly points to unseen mass, it means our cosmic maps are woefully incomplete, missing continents of matter that shape the universe from the shadows. Whether it's a hidden supercluster or evidence of realms beyond our own, this wall isn't just a structure, it's a question mark, challenging us to look deeper and wonder what else might be pulling the strings of the cosmos. Hidden in the southern constellation of Norma, a cosmic river flows, an invisible highway of galaxies stretching 150 million light-years across the void, all streaming toward the same inscrutable destination. This is the Norma cluster's filament, one of the most pivotal and perplexing structures in our galactic neighborhood. While massive walls and voids dominate headlines, this slender tendril of matter holds a far more intimate secret. It's the feeding tube for the great attractor, the mysterious gravitational anomaly that's pulling our entire galactic neighborhood toward an unseen fate. Picture a funnel gathering sand, except instead of grains, it's collecting galaxies, and instead of gravity, the pull comes from something far more enigmatic. The Norma filament acts like a galactic conveyor belt, channeling thousands of galaxies toward a point in space we can't even see, obscured behind the Milky Way's crowded disk. What makes this structure so extraordinary isn't its size, it's its function. While other filaments weave the cosmic web's scaffolding, this one serves a singular purpose, feeding the insatiable appetite of the great attractor, a gravitational anomaly so powerful it bends the paths of galaxies across hundreds of millions of light years. But here's the puzzle: the great attractor shouldn't be this strong. Based on the visible matter we've mapped the Norma cluster, the Centaurus supercluster, and other nearby giants, there's simply not enough mass to explain its gravitational grip. That's where the filament comes in. Recent studies suggest it's not just a passive bridge but an amplifier, funneling galaxies together so tightly that their combined gravity creates a deeper well than any single cluster could alone. It's like stacking magnets, individually weak but together unstoppable. Tracking this cosmic river wasn't easy. Astronomers had to peer through the zone of avoidance, that region of the sky where the Milky Way's dust and stars block our view. Using infrared and radio telescopes, they painstakingly mapped galaxy motions, revealing how entire clusters drift along this filament like leaves caught in a current. The data painted a clear picture. Everything, ourselves included, is being pulled toward the same invisible vortex, with the Norma filament serving as the primary artery. Yet the most fascinating twist lies in what we still don't know. The great attractor might not even be the final destination. Some research suggests it's just a waypoint on a longer journey, a stepping stone toward the even more massive Shapley supercluster, the largest concentration of matter in the observable universe. If true, the Norma filament isn't just feeding one mystery, it's part of a celestial breadcrumb trail, leading us deeper into the cosmic web's most hidden chambers. What's humbling is the scale of our motion. Thanks to this filament, our Milky Way, along with countless other galaxies, is hurtling toward the great attractor at over 600 kilometers per second, a speed that would take us from Earth to the Moon in just 10 minutes. And yet, we're so embedded in the flow that we barely notice, like ants on a drifting log, oblivious to the river carrying us toward an unseen horizon. The Norma filament is more than a structure, it's a reminder that even in the vastness of space, everything is connected. The same gravity that holds galaxies together also binds us to a destiny we're only beginning to uncover, one filament, one cluster, one irresistible pull at a time. Far beyond the reach of our most powerful telescopes lies the Shapley supercluster, a gravitational Goliath so massive it bends the flow of galaxies across the observable universe. Clocking in at 650 million light-years wide and containing more than 20 massive galaxy clusters, this cosmic colossus exerts a pull so strong it's dragging our entire local group toward it at 700 kilometers per second. That's like Earth orbiting the Sun at 8 times its current speed, a velocity so staggering it defies mundane comparison. But what makes Shapley truly fascinating isn't just its scale. It's the heated debate among astronomers about whether this supercluster alone can account for the mysterious bulk flow of galaxies in our cosmic neighborhood. At the heart of the controversy lies a simple question: is Shapley truly the universe's most powerful magnet, or are we missing something even larger? On one side of the debate stand researchers who argue Shapley's sheer concentration of mass equivalent to 10,000 Milky Ways easily explains the observed galaxy motions. They point to its dense core, where clusters like Abell 3558 pack hundreds of galaxies into a space just 20 million light-years across, creating a gravitational well deep enough to influence matter across intergalactic distances. Yet skeptics counter that math doesn't quite add up, that even Shapley's incredible mass falls short of accounting for the full strength of the dark flow dragging us toward it. The mystery deepens when we consider light's time delay. The Shapley supercluster we observe today is a snapshot from 700 million years ago, meaning its current position and mass remain unknown. Could it have merged with other superclusters in the interim, forming an even greater attractor? Some theorists speculate we might be seeing only the tip of the iceberg, that Shapley connects to a web of unseen mass extending beyond our observational horizon. Others propose more radical ideas, like the gravitational pull of parallel universes or exotic dark matter configurations. What's undeniable is Shapley's role in reshaping cosmic cartography. Before its discovery in the 1980s, astronomers assumed mass distribution was relatively uniform. Finding this supercluster was like discovering a mountain range where we'd expected flat plains, a revelation that forced us to redraw our maps of large-scale structure. Its gravitational tendrils may even connect to other giants like the Horologium Reticulum supercluster, forming a network of mass that spans billions of light years. For all its grandeur, the most humbling aspect of Shapley might be its impermanence. In another few billion years, as dark energy accelerates the universe's expansion, this supercluster will likely be the last island of structure in an ever-emptying cosmos, a final gathering place before the great cosmic diaspora scatters all galaxies beyond sight. Until then, it reigns as the largest confirmed mass concentration in our universe, a reminder that even the grandest structures are temporary waypoints in an evolving cosmic story. While the Shapley supercluster pulls galaxies toward the southern sky like a cosmic whirlpool, its northern counterpart, the Perseus-Pisces supercluster, forms a gravitational counterweight stretching 300 million light-years across the cosmos in a delicate balancing act. This sprawling network of galaxy clusters isn't just another structure. It's part of a cosmic seesaw, its mass tugging against Shapley's overwhelming gravity to create an invisible equilibrium that shapes the large-scale flow of our universe. Picture two teams in a tug-of-war, each anchored to opposite ends of the cosmos, with galaxies caught in the middle, drifting along the subtle currents between them. What makes Perseus-Pisces so fascinating isn't just its size, but its role in the universe's grand dynamics. Unlike the dense, hyper-concentrated core of Shapley, this supercluster unfurls like a vast celestial ribbon, weaving through constellations from Perseus to Pisces in a loose chain of galaxy clusters and filamentary bridges. Its structure is more distributed, less a monolithic fortress than a sprawling archipelago, with each cluster acting as a gravitational island in the cosmic web. Yet despite this fragmented appearance, its combined mass is staggering, exerting enough pull to offset a significant portion of Shapley's influence on our local universe. Scientists first mapped this counterbalance by studying peculiar velocities, the slight deviations in galaxy motions that can't be explained by universal expansion alone. When they plotted these subtle drifts, they found galaxies near Perseus-Pisces moving toward it, while those on the opposite side of the sky streamed toward Shapley, revealing an unseen equilibrium. It's like watching trees bend in opposite directions, revealing two competing winds we can't see. This discovery reshaped our understanding of cosmic flow, proving that even on scales of hundreds of millions of light-years, gravity's reach is finely tuned, with superclusters acting as the universe's great counterweights. But Perseus-Pisces holds another secret. It's a fossil from a younger, more violent cosmos. Many of its galaxies are older and quieter than those in Shapley, their star-forming gas long since exhausted in frenzied bursts of early creation. Some astronomers think this difference in temperament might trace back to their formation histories, where Shapley grew by cannibalizing smaller clusters in a chaotic feeding frenzy. Perseus-Pisces may have assembled more peacefully, its galaxies drifting together like leaves gathering in a calm eddy. The contrasting personalities of these two titans offer clues to how large-scale structure evolves, showing that even cosmic giants can take wildly different paths to maturity. What this supercluster teaches us is that balance reigns even in the grandest scales. The universe isn't just a chaos of random pulls. It's a dynamic interplay of forces where every great attractor has its counterweight, every colossal void its compensating wall. As we map more of these structures, we're discovering that the cosmos has a rhythm, a gravitational harmony where superclusters like Perseus Pisces don't just exist, they dance, locked in an eternal embrace with their counterparts across the void. And in that dance, we find the hidden order beneath the stars. While the Hercules-Corona Borealis Great Wall dominates headlines for its record-breaking scale, the Fornax Wall quietly shapes our cosmic neighborhood, a 150 million light-year filament of galaxies curving through the southern sky like a celestial spine. Nestled just 60 million light-years from Earth, this structure isn't just another thread in the cosmic web. It's a gravitational keystone, subtly warping the paths of nearby galaxies, including our own Milky Way. Picture a river bending trees along its banks, except here, the river is made of dark matter, and the trees are entire galaxies, their orbits subtly tilted by the wall's invisible pull. What sets the Fornax Wall apart isn't its size, but its intimacy. Unlike distant megastructures whose light takes billions of years to reach us, this wall is close enough that astronomers can study individual galaxies within it, watching how they interact with the filament's gravitational field. The wall's backbone is the Fornax cluster, a dense knot of galaxies where gravitational interactions are so intense they strip gas from smaller galaxies, leaving them red and dead, starved of the material needed to birth new stars. Yet just beyond this cluster, the wall frays into delicate tendrils, where spiral galaxies like our own float like leaves caught in a gentle current. The wall's true significance lies in its role as a cosmic crossroads. It intersects with the local void, a vast emptiness on our doorstep, creating a gravitational tension that shapes how galaxies move in our region. Recent studies suggest the Fornax Wall acts like a funhouse mirror, bending the trajectory of the local group's motion as we're pulled toward the great attractor. Without its counterbalancing influence, our galactic neighborhood might be hurtling even faster toward the Shapley supercluster, like a skier losing resistance on a downhill slope. Mapping this structure revealed an unexpected quirk. It's not uniform. Some sections are densely packed, with galaxies orbiting one another in tight loops, while others stretch thinly, their galaxies scattered like beads on a snapped string. This unevenness hints at a turbulent past, perhaps ancient collisions with smaller filaments, or the lingering imprint of dark matter fluctuations from the early universe. The wall isn't static, it's a living structure still evolving as galaxies migrate along its length, drawn toward the Fornax cluster's gravitational embrace. Yet the most tantalizing mystery is what the Fornax Wall might be hiding. Its proximity means much of it lies obscured behind the Milky Way's dusty disk in the so-called zone of avoidance. Radio telescopes have glimpsed hints of extensions curling toward the Eridanus supervoid, suggesting this wall could be part of a larger, unrecognized web, one that might rewrite our understanding of local cosmic geometry. Unlike the universe's record-breaking giants, the Fornax Wall doesn't dazzle with scale. Instead, it demonstrates how even modest structures can shape the cosmos in profound ways, reminding us that gravity's reach extends far beyond what's visible. In the grand tapestry of the cosmic web, it's not just the largest threads that matter. Sometimes the most influential ones are those woven closest to home. We think of outer space as vast and empty, but there's one void that hits particularly close to home. The local void, a sprawling 150 million light-year emptiness that isn't just sitting there quietly. It's actively pushing us away. This isn't passive nothingness, it's an expanding bubble of near vacuum, growing faster than the universe itself. and its gravitational influence is reshaping the motion of galaxies in our cosmic neighborhood, including our own Milky Way. Here's how it works. In the cosmic web, gravity isn't just about attraction, it's also about repulsion. While massive galaxy clusters pull matter toward them, voids like this one create a kind of anti-gravity effect. With so little mass inside, space itself stretches faster here, driven by dark energy's relentless push. The result, the local void isn't just empty, it's pushing outward, nudging galaxies along its edges like a snowplow clearing a path. And since we're perched on the void's border, that snowplow is shoving us too, accelerating the Milky Way and our neighboring galaxies toward denser regions of the universe at nearly 200 kilometers per second. This discovery flipped a long-held assumption on its head. Astronomers once thought our galaxy's motion was solely dictated by nearby attractors like the Great Attractor or the Shapley Supercluster. But the local void revealed another player in the game, one that doesn't pull but pushes. Imagine trying to walk across a trampoline while someone behind you stretches the fabric outward. Your path isn't just determined by the person in front of you tugging a rope, it's also shaped by the hollow expanding at your back. That's the delicate dance we're in, caught between the Great Attractor's pull and the local void's shove. The irony is rich. For centuries, humans believed we occupied an unremarkable corner of the cosmos. Now we've learned our address is special, not because of what's here, but because of what isn't. The local void's expansion makes our galactic neighborhood a frontier, a place where emptiness itself is an active force. And this isn't just a local quirk. Similar voids are stretching across the universe, each one contributing to the cosmic ballet of galaxy motions on scales we're only beginning to map. What's even wilder, the local void might not be done growing. As dark energy accelerates the universe's expansion, voids like this could stretch faster, eventually isolating galaxy clusters like islands in an ever-widening ocean of nothingness. For now, though, it serves as a reminder that even the emptiest places in the cosmos have a story to tell, one written not in starlight, but in the silent, insistent push of absence itself. Right now, the Virgo supercluster, our cosmic neighborhood spanning 110 million light-years, seems like an eternal fixture in the universe, but gravity has other plans. Over the next tens of billions of years, this vast collection of galaxy clusters, including our own Laniakea, won't just drift aimlessly. It's destined to collide, merge, and transform into something even grander. A mega structure so colossal it will redefine our place in the cosmos. The driving force behind this cosmic real estate deal is simple: gravity never sleeps. Already, the Virgo supercluster is being tugged toward the Great Attractor, a gravitational focal point hidden behind the Milky Way's dust. But that's just the first step. Beyond it looms the Shapley supercluster, the most massive concentration of matter we've mapped, a 650 million light-year wide behemoth with a gravitational pull that dominates our corner of the universe. Over eons, these titans will draw closer, their galaxy clusters weaving together like two immense spiderwebs merging into one. Here's where it gets mesmerizing. When superclusters collide, they don't crash like bumper cars. They perform a slow, gravitational waltz, galaxies slipping past one another, their paths bent by dark matter's invisible scaffolding. Picture two crowds merging in a stadium. Individuals don't collide, but the overall shape changes irrevocably. The Virgo and Shapley superclusters will stretch and deform, their filaments intertwining until they form a single, incomprehensibly large structure. Astronomers call this future behemoth the Laniakea Shapley hypercluster, a name that barely captures the scale of what's coming, but the real surprise. This hypercluster won't last forever. Dark energy, the mysterious force accelerating the universe's expansion, will eventually tear it apart. In the far future, any civilizations observing the sky will see only their local cluster as the rest of the universe vanishes beyond an unreachable horizon. For now, though, we're living in a golden age of cosmic connectivity, where gravity still holds sway over the largest structures in existence. The Virgo supercluster's fate isn't just a story of collision, it's a fleeting chapter in the universe's grand narrative, a reminder that even the mightiest structures are temporary waypoints in an ever-evolving cosmos. Most cosmic giants drift through space at the stately pace of universal expansion, but the Hercules supercluster bucks the trend. This 300 million light-year behemoth is sprinting sideways at nearly 500 kilometers per second, dragged off course by cosmic currents we can't yet see. That's like watching a cruise ship plowing through the ocean, only to suddenly veer as if pulled by some underwater force. This peculiar velocity, the difference between its expected and actual motion, isn't just a curiosity. It's a cosmic breadcrumb trail, hinting at hidden gravitational landscapes beyond the edges of our maps. What's yanking on something as massive as 20 quadrillion suns? The usual suspects nearby superclusters like Shapley or the Great Attractor don't fully account for Hercules' trajectory. Instead, astronomers suspect an even larger, unseen mass might be lurking in the so-called zone of avoidance, the region of sky obscured by our Milky Way's dust and stars. Imagine standing in a valley surrounded by mountains, but one peak is hidden behind fog. You can't see it, but you feel its presence in the way wildlife moves and rivers flow. Hercules' motion suggests our cosmic neighborhood might have a hidden mountain range, a concentration of mass so vast it warps the paths of superclusters like a magnet tugging at iron filings. The mystery deepens when we consider timing. Hercules' light takes over 300 million years to reach us, meaning we're seeing its position as it was when Earth's earliest dinosaurs roamed. By now, it could have traveled much farther along its cryptic path, or even changed direction entirely, caught in the crossfire of competing gravitational forces. Tracking its movement required painstaking analysis of thousands of galaxy redshifts, reconstructing velocities like forensic scientists piecing together a cosmic hit and run. The data reveals a startling pattern. Entire galaxy clusters within the supercluster share this anomalous drift, as if Hercules is a fleet of ships sailing toward the same invisible horizon. Some theorists propose a radical explanation, that Hercules might be responding to the gravitational pull of structures beyond our observable universe. According to this idea, the Big Bang's initial conditions could have created density variations so vast that their edges extend past our cosmic horizon, tugging on matter we can see from realms we'll never glimpse. It's like sensing ocean tides from a sealed submarine. You know the force is there, but the source remains forever out of view. Other scientists counter that simpler explanations exist. Perhaps undiscovered superclusters or exotic dark matter configurations could explain the anomaly without invoking unobservable domains. What makes Hercules' dance so compelling is what it reveals about our blind spots. For all our telescopic prowess, we still see less than 10% of the sky's total mass due to galactic obstruction. This supercluster's motion forces us to confront how much we're missing, how the cosmos might be threading needles of gravity through the very regions we struggle to observe. Whether the culprit is a hidden supercluster or something stranger, Hercules reminds us that the universe's largest structures aren't just static landmarks, they're travelers on an epic journey, and their paths may lead to discoveries we haven't even imagined. Named for the water-bearer constellation it inhabits, the Aquarius supercluster flows through the cosmos like a celestial river, a sprawling network of galaxies spanning 250 million light-years, with currents of dark matter weaving through its depths. But don't let the tranquil name fool you. This supercluster is a cosmic oddity, defying expectations with a lopsided population of galaxies that reads more like a misfit toy box than the orderly gatherings we're used to. Where most superclusters host a balanced mix of spiral and elliptical galaxies, Aquarius skews wildly toward ancient, red elliptical galaxies so starved of star-forming gas they glow like embers in the cosmic dark. So why does Aquarius play host to this geriatric galactic crowd? The answer might lie in its environment. Nestled at a crossroads of cosmic filaments, this supercluster sits where multiple rivers of matter converge, creating a gravitational pressure cooker. When galaxies are funneled into such dense quarters, they collide and merge at breakneck speeds, stripping away the gas needed to birth new stars. Over time, these encounters transform spirals, those vibrant star-making factories, into elliptical husks. Picture a bustling city square where street performers spiral galaxies, get swallowed up by corporate high-rises ellipticals, until only the monolithic giants remain. That's Aquarius, a supercluster that traded its cosmic diversity for gravitational efficiency. Yet even among its sea of red giants there are rebels. Scattered along the supercluster's fringes, astronomers have spotted a handful of stubborn spirals clinging to their gas reserves like desert oases. These outliers might hold clues to Aquarius' past. Some researchers suspect they're newcomers, galaxies that arrived late to the supercluster's gravitational party and haven't yet been stripped of their star-forming potential. Others propose a darker twist, that the supercluster's core is so saturated with hot plasma, it acts like a cosmic griddle, slowly evaporating gas from any galaxy daring to wander too close. What makes Aquarius truly fascinating, though, is its silence. In younger superclusters, you'd expect the crackle of radio emissions from fresh black hole activity or the ultraviolet glow of newborn stars. But Aquarius hums at lower frequencies, its galaxies dominated by the faint infrared warmth of aging stars. It's as if the supercluster hit the cosmic pause button eons ago, its story written in the quiet fade of countless suns. But here's the twist: this tranquility might be temporary. Simulations suggest Aquarius is on a collision course with the neighboring Piscis-Pavo supercluster, a slow-motion merger that could reignite star formation in some galaxies as their gas reserves are jostled awake. It's a reminder that even the sleepiest corners of the universe are never truly static, just waiting for the next gravitational spark to rewrite their future. For now, Aquarius stands as a cosmic cautionary tale, a glimpse of what happens when galaxies gather too close, too fast, and trade their vitality for the cold comfort of the crowd. Tucked between the Virgo and Coma superclusters, the Leo spur isn't just a bridge, it's a cosmic tightrope, a delicate filament of galaxies threading the void across 100 million light-years. Picture a rope strung between two skyscrapers swaying in the wind. Now replace the rope with a chain of galaxy clusters and the skyscrapers with titanic superclusters, each weighing quadrillions of suns. That's the Leo spur, a fragile yet vital connection in the universe's grand design, proving that even the vastest structures are linked by threads thinner than we ever imagined. What makes this spur extraordinary isn't just its length, it's the precision of its placement. Gravity could have flung these galaxies into chaos, yet they cling to this narrow path like pearls on a necklace, tracing a route between two of the most massive gatherings of matter in our cosmic neighborhood. The Virgo supercluster, our galactic home, anchors one end, while the Coma supercluster, a dense hive of thousands of galaxies, looms at the other. Between them, the Leo spur acts as a lifeline, funneling galaxies and gas along a gravitational highway that's been bustling with traffic for billions of years. But here's the puzzle: bridges like this shouldn't survive intact. The universe's expansion should stretch and snap such delicate filaments over time. Yet the Leo spur endures, its galaxies moving in eerie synchrony. The secret might lie in dark matter, the invisible scaffolding of the cosmos. Simulations suggest this spur could be wrapped in a sheath of dark matter, a hidden exoskeleton that stabilizes its structure against the tides of expanding space. It's as if the universe reinforced this bridge with cosmic steel cables, invisible to us but vital to its integrity. The spur's galaxies tell their own story. Unlike the ancient red giants crowding supercluster cores, many here are younger, bluer, and still rich with star-forming gas. This isn't a retirement home for aging stars. It's a galactic frontier where fresh batches of matter stream in from the voids, fueling new stellar nurseries. Some astronomers compare it to a rural highway dotted with small towns, where the slow trickle of resources keeps life humming, far from the dense urban centers of Virgo and Coma. Yet the Leo spur's greatest lesson might be about connectivity. In the cosmic web, nothing exists in isolation. The spur isn't just a curiosity, it's proof that even the mightiest superclusters are part of something larger, tied together by filaments that channel matter and energy across the universe. And if such delicate threads can shape the fate of galaxies, what other subtle connections might we be missing, hidden in the spaces between the stars? The answer could rewrite our understanding of how the universe builds its largest structures, one fragile bridge at a time. While most superclusters pull galaxies toward them like cosmic magnets, the Pavo-Indus supercluster plays a different game. This sprawling southern structure isn't just attracting matter, it's part of a colossal tug of war with something far stranger, the dipole repeller, a near-empty region of space so devoid of mass it pushes galaxies away. Picture a seesaw where one side is weighted with galaxies and the other is an almost perfect vacuum, creating a balance of forces that shapes how everything moves in our corner of the universe. This 200 million light-year-wide supercluster, rich with galaxy clusters like Pavo and Indus, isn't just a gravitational anchor. It's one half of a cosmic equilibrium, countering the repeller's void to steer the motion of our local group and countless other galaxies. What makes this dynamic so fascinating is how it upends our intuition about gravity. We're used to thinking of mass as the sole driver of cosmic motion, but the dipole repeller proves that absence can be just as powerful. Located roughly 700 million light-years away in the opposite direction from Pavo-Indus, this void's lack of gravitational pull allows space itself to expand faster there, creating a kind of anti-attractor that shunts galaxies toward denser regions. It's like walking uphill only to find the ground behind you collapsing faster than you can climb. The void's repulsion is just as critical to our galactic trajectory as the supercluster's pull. Scientists pieced together this puzzle by mapping the peculiar velocities of thousands of galaxies, the subtle deviations in their motion that can't be explained by universal expansion alone. The data revealed a clear pattern. Galaxies weren't just streaming toward Pavo-Indus, they were also being pushed away from the dipole repeller, caught in a cosmic current between these two extremes. This duality reshaped our understanding of large-scale flows, proving that the universe's architecture isn't just built on where matter is, but also where it isn't. But here's the twist: the dipole repeller isn't some special anomaly. Voids like it are everywhere, each one contributing to the intricate dance of galaxies. Pavo-Indus stands out because it's exceptionally massive, making its balancing act with the repeller visible across intergalactic distances. Together, they form a dipole, a pair of opposing influences that act like cosmic signposts, guiding the bulk flow of galaxies in our vicinity. It's a reminder that the universe's grand design relies on both presence and absence, with superclusters and voids working in tandem to sculpt the paths of everything within them. The takeaway: even the emptiest corners of space have a voice in the cosmic chorus. Pavo-Indus might be the star of this show, but its performance only makes sense alongside the silent, pushing force of the dipole repeller. In the end, it's not just about where galaxies gather. It's about the hollows between them, the voids that shape the universe as surely as its brightest lights. The Centaurus supercluster isn't just another gathering of galaxies, it's the gravitational linchpin in one of the universe's greatest mysteries, the Great Attractor. Spanning 200 million light-years, this colossal structure sits at the crossroads of cosmic motion, its mass equivalent to 100,000 Milky Ways tugging at everything in our galactic neighborhood. But here's what's wild: for decades we couldn't even see its full scope. Hidden behind the Milky Way's dusty disk, the Centaurus supercluster's true heft only came into focus when astronomers turned to X-ray telescopes, revealing a hidden metropolis of galaxy clusters glowing with superheated gas. Those X-ray observations cracked the case wide open. By mapping the faint glow of million-degree plasma between galaxies, scientists uncovered a gravitational powerhouse far denser than optical surveys had suggested. The gas isn't just floating idly, it's trapped in deep wells of dark matter, its searing heat betraying the presence of invisible mass. This invisible scaffolding amplifies the supercluster's pull, making it the primary engine behind the great attractor's infamous drag. Picture a magnet buried in sand. You might spot a few iron filings on the surface, but it's the hidden bulk below that's really doing the work. Yet the Centaurus supercluster isn't acting alone. It's part of a grander conspiracy of gravity, linked to the Norma cluster and the Hydra Centaurus complex, forming a sprawling mass that bends the paths of galaxies like a cosmic whirlpool. Recent studies suggest this system might weigh twice as much as early estimates, with some filaments stretching toward the even larger Shapley supercluster. That's the irony. The great attractor isn't a single thing but a confluence of forces, a gravitational nexus where multiple superclusters pool their influence. What's haunting is the timescale. The light we see from Centaurus left when dinosaurs still ruled Earth, meaning the supercluster's current position and its gravitational grip could be vastly different now. By the time its photons reach us, the cosmos has already moved on. Yet even this delayed snapshot reshapes our place in the universe. We're not just drifting aimlessly, we're caught in a river of galaxies, flowing toward a destination shaped by giants like Centaurus, a reminder that the largest structures don't just fill space. They orchestrate its motion. Looming in the northern sky like a half-finished sculpture, the Draco supercluster defies every expectation of what a massive structure should look like. While most superclusters boast dense galactic metropolises, this sprawling 500 million light-year network feels almost unfinished, its galaxies scattered like lonely outposts across a cosmic frontier. This isn't just a difference in scale, it's a masterclass in how environment shapes destiny. Where richer superclusters like Shapley or Laniakea team with galaxies colliding and merging in gravitational chaos, Draco's residents float in quiet isolation, their evolution slowed by the emptiness around them. The secret to Draco's sparse nature lies in its address. This supercluster resides in what astronomers call a low-density field, a cosmic neighborhood where the raw materials for galaxy building were scarce from the start. Picture two cities, one built at the intersection of fertile rivers, the other in a desert. Both may grow, but their trajectories diverge wildly. Draco's galaxies formed where the primordial soup of matter was thinner, leaving them starved of the gas and dark matter needed to build dense clusters. The result, a supercluster that looks more like an archipelago than a continent, with vast gulfs of nothingness separating its few galactic islands. This isolation has profound effects. Without frequent collisions to trigger star formation, Draco's galaxies age differently. Many are red and dead, elliptical relics where star birth ceased billions of years ago, their remaining stars slowly burning out in quiet desperation. Others are backsplash galaxies, stragglers that once passed through a cluster core and were flung back into the void, their gas stripped away by the encounter. It's a galactic retirement home where the quiet is deafening and the pace of change glacial. Yet Draco's loneliness makes it invaluable to science. By studying how galaxies behave without the constant turbulence of crowded clusters, astronomers can isolate the effects of environment like never before. Here, galaxies evolve primarily through internal processes, their gas reservoirs slowly depleted by star formation rather than ripped away by neighbors. Some even harbor extended disks of hydrogen gas, fragile structures that would have been shredded in busier superclusters. These pristine galaxies act as control groups, helping scientists disentangle nature from nurture in cosmic evolution. The most fascinating twist, Draco might not always be this quiet. Simulations suggest it's part of a larger filament flowing toward the Hercules supercluster, a gravitational current that could eventually merge these sparse regions with denser structures. If so, Draco's galaxies may yet get a second act, a late-stage collision course that reignites star formation and shakes this sleepy supercluster awake. For now, though, it stands as a reminder that the universe doesn't just build giants, it also carves out quiet corners where galaxies can grow old in peace, their stories unfolding at the pace of the void itself. Stretching across the constellations of Pegasus and Pisces like a celestial necklace, the Pegasus-Pisces chain weaves through the cosmos, a 300 million light-year filament of galaxy clusters that perfectly embodies the universe's intricate architecture. Unlike the dense, knotty cores of superclusters, this structure is all about flow, a graceful arc of matter tracing the invisible scaffolding of the cosmic web. Picture a river of galaxies, each cluster a glowing buoy bobbing in the current of dark matter's unseen tide. What makes this chain so captivating isn't just its length, but its textbook perfect alignment with how theorists predict filaments should form, delicate, elongated, and threaded along the universe's gravitational seams. The chain's existence is a triumph of cosmic evolution. Billions of years ago, tiny quantum fluctuations in the newborn universe, smaller than a single atom, snowballed into density variations, regions where dark matter pooled ever so slightly thicker. Over eons, gravity amplified these ripples, drawing gas and galaxies into sprawling tendrils. The Pegasus-Pisces chain is one such tendril, a fossilized ripple grown unimaginably large. Its galaxies didn't randomly scatter, they're strung along the spine of an ancient dark matter filament, drawn together like iron filings along a magnet's field lines. Yet there's a twist. While most filaments feed matter into superclusters like tributaries flowing into a lake, this chain feels oddly self-contained, a bridge between two cosmic voids rather than a feeder line. Some astronomers speculate it might be a relic from an era before superclusters fully formed, a snapshot of the universe's adolescence when filaments were the dominant structures. Others suggest it's evidence of a rare, stalled filament, a thread that never fully funneled its galaxies into a denser knot, leaving them suspended in this delicate, linear balance. Mapping the chain reveals another curiosity. Its galaxies are aging unevenly. Near the center, where gravitational interactions are strongest, elliptical galaxies dominate, their star-forming gas stripped away by ancient collisions. But toward the fringes, spirals still thrive, their disks rich with young, blue stars. This gradient isn't just a quirk, it's a living lesson in how environment shapes galactic destiny. The chain structure acts like a timeline, showing how galaxies evolve as they march along filaments toward denser regions, trading vibrancy for gravitational security. What's truly humbling is the scale of our perspective. From Earth, the Pegasus-Pisces chain appears as a two-dimensional smudge across the sky. Only by measuring redshifts, the stretching of light as galaxies race away from us, can we reconstruct its three-dimensional arc, a curve so vast it would take light 300 million years to travel from one end to the other. And even then, we're seeing it as it was in the distant past, its light a postcard from an era when galaxies were still learning their place in the cosmic web. Ultimately, this chain isn't just a structure, it's a bridge between theory and observation. For decades, simulations predicted filaments like this should exist, but seeing one so pristine, so elegantly aligned with the cosmic web's blueprint feels like uncovering a Rosetta Stone of large-scale structure. It's a reminder that the universe doesn't just build in chaos, it weaves order on scales so grand we're only beginning to trace the pattern. Hovering in the northern sky like a celestial crown, the Corona Borealis supercluster isn't just another gathering of galaxies, it's a cosmic oddity, a 300 million light-year-wide ring of galaxy clusters that defies the usual rules of cosmic architecture. While most superclusters sprawl in loose, web-like filaments, this one curves into a near-perfect arc, as if some unseen hand traced a circle across the void and galaxies obediently followed. The strangest part, this geometry shouldn't exist. Gravity doesn't naturally sculpt matter into rings on such colossal scales unless something extraordinary happened here billions of years ago. One leading theory suggests the supercluster's shape might be a fossilized echo of an ancient collision, a cosmic fender bender of unimaginable proportions. Picture two massive proto-superclusters, each a tangle of dark matter and young galaxies, slamming into each other in the universe's wild adolescence. The impact wouldn't have been a head-on crash but a grazing blow, sending shockwaves rippling through the surrounding gas and dark matter like a stone skipping across a pond. Over eons, those ripples could have sculpted the debris into a ring, with galaxies piling up along the crest of the wave like foam on a shoreline. Simulations show such collisions can create temporary ring-like structures, but finding one preserved in the modern universe is like stumbling upon a dinosaur footprint perfectly intact after millennia of erosion. But there's a darker possibility. Some astronomers speculate the supercluster's shape might not be a collision scar but a gravitational illusion, a trick of perspective where multiple filaments in the cosmic web align just right to form a curve from our vantage point. If true, it's a cosmic mirage on an epic scale, a reminder that even the largest structures can deceive us when seen from the wrong angle. Yet detailed redshift surveys argue against this. Galaxies in the Corona Borealis ring share similar velocities, suggesting they're genuinely bound together in this peculiar configuration, not just strung along by chance. What makes this supercluster truly fascinating is its personality. Unlike the dense, chaotic cores of most superclusters, Corona Borealis ring feels oddly balanced, its galaxies spaced like jewels in a royal diadem. The largest cluster, Able 2065, sits at the crown's apex, weighing in at a quadrillion solar masses, while smaller clusters and groups dot the circumference. This isn't a hierarchy but a democracy of gravity where no single cluster dominates. The arrangement slows down galactic evolution. Without a dense core to stir up collisions, many galaxies here have aged quietly, their star formation fading gently rather than being violently quenched. The supercluster's light reaches us from an era when the universe was two-thirds its current age, offering a snapshot of a time when large-scale structures were still settling into their modern forms. By now, the ring may have distorted further, its symmetry frayed by dark energy's push or mergers with other filaments, or perhaps against all odds. It's held its shape, a cosmic monument to that long-ago collision, a reminder that even the universe's grandest designs can be born from chaos. Either way, Corona Borealis challenges us to rethink how gravity sculpts the cosmos, proving that sometimes the most elegant structures emerge from the most violent beginnings. Just beyond our cosmic doorstep, a mere 50 million light-years away floats the Sexton's Cloud, a gauzy, ghostly structure that shouldn't exist. Unlike the crisp spirals and blazing ellipticals we're used to, this cloud is a cosmic paradox, a loose, shapeless swarm of stars and gas, barely held together by gravity, yet teeming with enough dark matter to stop theorists in their tracks. If most galaxies are bustling cities, the Sexton's Cloud is a fog of distant streetlights, flickering in the void with no apparent center or reason. But here's the twist. This faint, sprawling enigma contains 6 times more dark matter than visible stars, a ratio so extreme it's forcing astronomers to rethink how galaxies are born. Dark matter is the universe's invisible scaffolding, the glue that binds galaxies together. Normally, it works in tandem with visible matter stars and gas, pulling them into familiar shapes like spirals or ellipticals. But the Sexton's Cloud breaks the mold. Its stars are scattered so thinly that by all rights they should have drifted apart eons ago. The fact they haven't suggests something extraordinary. This cloud's dark matter isn't just present, it's overwhelming, an invisible ocean with only a few scattered islands of light floating atop it. Imagine a fishing net with weight so heavy they could anchor an entire harbor, yet only a handful of buoys marking where they lie. That's the Sexton's Cloud, a dark matter colossus wearing a stellar disguise so faint we almost missed it entirely. What's baffling is how such a structure could form. Current simulations suggest galaxies grow when dark matter halos pull in gas, which then condenses into stars. But the Sexton's Cloud's dark matter halo seems to have failed at its job, gathering just enough gas to sputter out a few stars before giving up. Some theorists propose it's a failed galaxy, a cosmic stillbirth where star formation stalled before it could truly begin. Others wonder if it's the remnant of a larger galaxy ripped apart by tidal forces, its stars scattered but its dark matter left eerily intact. The truth might lie in the cloud's environment. It drifts near the edge of the local void, a vast, empty region where intergalactic gas is scarce. Without enough fuel to ignite starbirth, the Sexton's Cloud could be a relic of cosmic austerity, a structure that starved before it could shine. Yet this cloud's greatest significance might be what it reveals about dark matter itself. Its extreme mass ratio hints that dark matter doesn't always cluster where visible matter does, that it can pool in places we'd never think to look, shaping the cosmos in ways our telescopes can't directly see. If there are more structures like this lurking in the shadows, our census of the universe's mass could be wildly incomplete. The Sexton's Cloud isn't just a curiosity. It's a challenge, a whisper from the darkness asking us to reconsider everything we thought we knew about how galaxies and the unseen forces that shape them really work. For decades, astronomers mapped the cosmos with a glaring blind spot. An entire wall of galaxies, 150 million light-years long, hiding in plain sight. The Antlia Wall lurked just beyond our view, cloaked behind the thick dust and stars of our own Milky Way, a cosmic phantom in the southern sky. It wasn't until advanced radio and infrared telescopes pierced through this galactic veil that we finally saw the truth, a sprawling filament of galaxy clusters, each one a glittering island in the dark, strung together like pearls on an invisible thread. What makes the Antlia Wall so fascinating isn't just its scale, it's the irony of its obscurity. While astronomers peered billions of light-years away to discover far more distant structures, this colossal neighbor remained practically on our doorstep, obscured by the same cosmic debris that makes the Milky Way's center glow so brilliantly. Imagine living next to a mountain range for years and never realizing it was there because of a stubborn fog. That's how close we were to missing one of the largest nearby structures in the universe. The breakthrough came when scientists turned from visible light to wavelengths that could penetrate the dust. Radio telescopes like Parkes and Mercator detected the faint whispers of hydrogen gas in Antlia's galaxies, while infrared observations from space-based telescopes like Spitzer revealed their heat signatures cutting through the cosmic smog. Slowly, the wall's outline emerged, a vast, curving sheet of galaxies, stretching from the Antlia cluster to the edge of the Hydra Centaurus supercluster, a bridge between two gravitational titans. But here's the twist: the Antlia Wall isn't just a passive bridge. Its galaxies are caught in a slow-motion migration, flowing toward the Norma cluster, the heart of the great attractor, like leaves drifting downstream. This motion hints at something deeper. The wall might be part of a larger current, a conveyor belt of matter feeding the most mysterious gravitational anomaly in our cosmic neighborhood. The most humbling realization: if something this massive could hide so close by, what else might we be missing? The universe has a way of reminding us that even our best maps are still full of uncharted territory, waiting for the right tools and the right perspective to reveal their secrets. While the local void expands like an ever-widening hole in space, pushing galaxies away with its emptiness, the Columbus supercluster tells the other half of the story. A sprawling network of galaxies caught in a cosmic tug-of-war, fleeing the void's grasp at nearly 200 kilometers per second. This isn't just a random drift. It's a celestial exodus, a slow-motion stampede where entire galaxy clusters are being herded by the absence of gravity itself. Picture a crowd recoiling from an invisible force, their motion betraying something unseen. That's the eerie dynamic playing out here, where the superclusters galaxies aren't being pulled towards something but pushed by nothingness. What makes Columbus so compelling is its role as a cosmic barometer, revealing how local expansion warps space in ways that defy intuition. Most of the universe's growth is uniform, like dough rising in an oven, except where voids like ours stretch faster, creating uneven pockets where relativity gets weird. The superclusters galaxies act as tracers, their velocities revealing the void's repulsive effect. Imagine floating in a river where the water ahead suddenly vanishes and the current behind you surges forward. That's the gravitational imbalance driving Columbus' motion. But here's the twist: Columbus isn't just running from the local void. It's also being drawn toward the Shapley supercluster, the most massive concentration of matter in our observable universe. This dual influence creates a fascinating paradox: galaxies caught between the push of nothing and the pull of everything. The result, a supercluster stretched like taffy, its shape distorted by competing forces. Some regions stream toward Shapley in tight filaments, while others sprawl outward, resisting the void's expansion. It's a living lesson in how cosmic structures aren't just passive objects, but dynamic players in a gravitational drama. The most startling insight comes from Columbus' galaxies themselves. Unlike denser superclusters where collisions run rampant, these galaxies are aging in isolation, their star formation slowing as they drift farther apart. It's as if the void's push is preserving them in cosmic amber, freezing their evolution in a way that crowded clusters never could. Astronomers call this void galaxy phenomenon a rare chance to study how environment shapes destiny. Some of Columbus' loneliest galaxies still cling to vast reservoirs of hydrogen gas, untouched by the violent interactions that strip such fuel away in busier regions. Yet Columbus' fate is far from static. Over billions of years, the local void's expansion will accelerate, driven by dark energy's relentless push. The superclusters galaxies may one day find themselves truly unmoored, isolated islands in an ever-widening gulf. For now, though, they're a snapshot of cosmic tension, a reminder that even emptiness has a voice in the universe's grand narrative, and that the largest structures are shaped as much by what's missing as by what's there. Nestled between the Lynx and Cancer constellations lies one of the most perplexing gaps in the cosmic map. The Lynx-Cancer void, a 200 million light-year chasm that appears almost entirely devoid of galaxies. At first glance, it resembles the Boots void, another infamous cosmic desert, but here's where the mystery deepens. Unlike Boots, which hosts at least a few dozen galaxies, the Lynx-Cancer void seems too empty, pushing the limits of what our models of cosmic structure predict. Some astronomers argue this region is a true vacuum, a near-perfect nothingness that challenges our understanding of how matter distributes itself across the universe. Others suspect it's an illusion, a trick of observation where dust, foreground stars, or survey limitations create the appearance of absence where there might actually be faint, undiscovered galaxies. The debate hinges on a fundamental question: how empty is space allowed to be? According to the standard model of cosmology, matter should clump unevenly, but not to the extreme we seem to be seeing here. Voids are common, but one this vast and barren strains credibility. Simulations of the cosmic web predict voids no larger than 150 million light-years, yet Lynx-Cancer dwarfs that. If it's genuinely as empty as it appears, it might hint at exotic physics, perhaps primordial quantum fluctuations in the early universe left behind regions so underdense that not even dark matter could gather enough material to form galaxies. But there's another possibility. Our tools just aren't seeing the whole picture. The void lies along a sightline crowded with Milky Way dust, which dims distant galaxies and makes them harder to detect. Modern surveys like the Sloan Digital Sky Survey have gaps in coverage here, meaning galaxies could be lurking undetected. Radio telescopes which peer through dust have spotted a handful of ultra-diffuse galaxies in similar voids, ghostly, low-brightness systems that optical surveys miss. If Lynx Cancer holds such faint inhabitants, its emptiness might be an observational blind spot rather than a cosmic anomaly. What's fascinating is how this void defies categorization. If it's real, it reshapes our understanding of structure formation. If it's an illusion, it highlights how much we still rely on imperfect tools to map the cosmos. Either way, Lynx Cancer forces us to confront the limits of our knowledge and the humbling truth that sometimes the universe's most profound mysteries aren't found in its brightest objects, but in the shadows between them. Tucked away in the constellation of Calum, the sculptor's chisel, lies one of the most enigmatic superclusters we've ever discovered, a 400 million light-year behemoth glowing with an eerie excess of quasars, the universe's most luminous object. The Calum supercluster doesn't just host these brilliant beacons, it's drowning in them, packing more quasars into its sprawling framework than any structure of its size should theoretically hold. This isn't just a cosmic curiosity, it's a smoking gun, pointing to a violent past where galaxies didn't just drift together but slammed into one another with enough force to awaken the sleeping giants at their cores. Quasars are the universe's ultimate powerhouses, supermassive black holes gorging on gas so furiously they outshine entire galaxies. Normally, they're rare, scattered across the cosmos like distant lighthouses. But in Calum, they're practically neighbors, blazing in numbers that defy conventional models of structure formation. The leading theory, this supercluster is a fossilized battlefield, the remnant of an ancient cosmic pileup where multiple galaxy clusters collided in a gravitational frenzy. When galaxies merge, their central black holes can be jolted awake, sucking in vast amounts of matter and igniting as quasars. In Calum, it seems this happened on a staggering scale, not just once, but repeatedly, as dense knots of galaxies crashed together over billions of years. Here's where it gets even stranger. The quasars in Calum aren't randomly scattered, they're clustered along filaments, tracing the supercluster's hidden skeleton like Christmas lights strung along a wire. This alignment suggests the collisions weren't chaotic but channeled, funneled by the same dark matter tendrils that sculpt the cosmic web. Picture a highway where galaxies don't just travel, they wreck, piling into one another at intergalactic speeds, each collision sparking a new quasar in the chain. But Calum's true significance lies in its timing. The light we see from its quasars is ancient, emitted when the universe was barely half its current age. That means we're witnessing the aftermath of collisions that happened eons ago, frozen in starlight. By now, those quasars have likely faded, their black holes starving into silence as they exhausted their fuel. Yet their lingering glow offers a rare window into an era when the universe was wilder, denser, and far more violent, a time when superclusters weren't just gathering but clashing, forging their shapes in chaos. The most tantalizing question isn't just how Calum formed, but whether it's unique. If such quasar-rich superclusters were common in the early universe, they could have seeded the largest structures we see today, their collisions laying the groundwork for modern cosmic architecture. Or perhaps Calum is an outlier, a rare relic of a universe that preferred its growth spurts explosive and its black holes wide awake. Either way, this distant supercluster reminds us that the cosmos doesn't just build, it collides, and from those collisions, new wonders emerge. The Delphinus Void isn't just another empty patch of space, it's a geometric oddity, a near-perfect sphere of nothingness stretching 100 million light-years across, as if someone took a cosmic cookie cutter to the universe. Most voids resemble lumpy bubbles or irregular gaps in the cosmic web, their shapes warped by surrounding filaments and clusters. But Delphinus defies convention, its eerie symmetry so precise it almost feels artificial. This isn't just a hole in the galaxy distribution. It's a celestial riddle challenging our understanding of how emptiness takes form in the cosmos. The mystery begins with its origin. Standard void formation theories suggest these regions grow from tiny underdensities in the early universe, places where matter was slightly sparser than average. Over billions of years, gravity amplified these differences, pulling matter toward denser regions and leaving behind ever-expanding voids. But those models predict irregular shapes, not perfect spheres. For Delphinus to achieve such symmetry, something extraordinary must have happened. A gravitational ballet where every external pull cancelled out, or perhaps a primordial fluctuation so finely tuned it defies statistical odds. Some theorists even speculate this void could be the scar of an ancient collision between two universe-sized bubbles in the multiverse, their intersection leaving behind a vacuum as smooth as a soap bubble surface. What's equally puzzling is what's not inside Delphinus. Most voids contain a handful of lone void galaxies, isolated stragglers drifting through the emptiness like shipwrecks in an ocean. But Delphinus is nearly pristine, its interior so vacant that astronomers debate whether any galaxies exist there at all. The few candidates detected along its edges appear peculiarly undisturbed, their gas reservoirs intact and star formation churning quietly, as if the void's perfect emptiness somehow sheltered them from the usual violence of cosmic evolution. It's as if Delphinus isn't just empty, it's preserved, a cosmic snow globe where time moves differently. The void's spherical perfection might also hold clues to dark energy's influence. As the universe expands, voids grow faster than denser regions, their emptiness offering less resistance to dark energy's push. Delphinus' shape suggests this expansion could be remarkably uniform here, with none of the gravitational tugs from surrounding clusters that typically distort voids into lumpy, asymmetrical forms. If true, this void might be a rare laboratory for studying dark energy's purest effects, a place where the universe's acceleration isn't muddied by the chaos of matter. Yet the most haunting possibility is that Delphinus isn't unique, just the first of its kind we've noticed. If similarly perfect voids exist, they could rewrite our cosmic playbook, hinting at forces or initial conditions we've yet to imagine. For now, this sphere of nothingness floats silently in the depths of space, a reminder that even emptiness holds secrets, and the universe's simplest shapes can be its most profound mysteries. Hovering in the southern skies, the Volans Puppis supercluster weaves a cosmic mystery, a sprawling network of galaxies spanning 250 million light-years, its motion defying expectations. While most superclusters drift lazily with the universe's expansion, this one seems caught in a current, its galaxies streaming in a coordinated flow that doesn't match the pull of any known structure. The anomaly isn't just in its movement but in its light. Redshift measurements, the telltale stretching of wavelengths that reveal cosmic motion, don't line up. Some galaxies appear to race toward us while others flee, creating a conflicting map that leaves astronomers scratching their heads. At the heart of this puzzle is the dark flow, a controversial phenomenon where large-scale structures exhibit unexplained bulk motion, as if tugged by something beyond our observable universe. Volans Puppis fits eerily into this pattern. Its galaxies don't follow the predictable paths dictated by neighboring superclusters like Shapley or the Great Attractor. Instead, they skew toward a point in space devoid of known mass, suggesting an unseen gravitational hand at work. Picture a river suddenly diverting away from a mountain, inexplicably drawn toward an invisible valley. That's the kind of cosmic defiance we're dealing with here. The redshift discrepancies only deepen the intrigue. Normally, galaxies in a supercluster share similar velocities, their light uniformly shifted by the collective pull of the structure's gravity. But in Volans Puppis, the data scatters wildly. Some galaxies show redshift suggesting they're receding faster than the universe's expansion should allow, while others appear nearly stationary, as if locked in place by unseen forces. One theory points to the supercluster's complex geometry. It might not be a single cohesive structure but a chance alignment of multiple filaments, each with its own dynamic. Another, more radical idea proposes that we're seeing the gravitational imprint of a parallel universe, its mass warping our space-time from beyond the cosmic horizon. What's especially tantalizing is the supercluster's placement. It sits along the same axis as other dark flow anomalies, including the Grooves Wall and parts of the Centaurus supercluster, as if these structures are all caught in the same invisible tide. If confirmed, this alignment could rewrite our understanding of large-scale cosmic motion, hinting at forces or realms beyond current physics. Yet skeptics argue the conflicting redshifts might stem from observational noise, dust clouds, instrumental error, or the simple challenge of mapping such distant galaxies through the Milky Way's crowded disk. Regardless of the explanation, Volon's puppy stands as a reminder that the universe's grandest structures don't always play by the rules. Their motions, shapes, and even light may hold clues to mysteries we've only begun to name, whether hidden dimensions, undiscovered mass, or flaws in our deepest theories. For now, this supercluster drifts in the southern sky, a silent rebel whose secrets remain just out of reach. Tucked away in the southern skies, far from the dense galactic metropolises we often study, lies the Tucana supercluster, a sprawling network of galaxies stretching over 300 million light-years, quietly reshaping one of cosmology's fiercest debates. This isn't just another gathering of stars, it's a cosmic courtroom where two competing theories, dark matter and modified gravity, face off, with Tucana's peculiar dynamics serving as the star witness. What makes Tucana so pivotal is its defiance of expectations. According to conventional dark matter models, superclusters should move predictably, their galaxies orbiting in stately harmony under the invisible grip of dark matter's gravitational pull. Yet Tucana's galaxies drift with a rhythm that doesn't quite match the score. Their velocities, painstakingly mapped through redshift surveys, suggest something unexpected. Either dark matter is distributed in ways our models can't explain, or gravity itself behaves differently on these colossal scales. Enter modified Newtonian dynamics, a radical theory proposing that we've misunderstood gravity all along. Instead of invoking unseen dark matter, suggests gravity strengthens slightly where its pull would typically weaken, an adjustment that could explain galactic motions without hidden mass. Tucana's galaxies, with their unanticipated speeds and trajectories, align eerily well with predictions. It's as if the supercluster is a living experiment, testing whether the universe's largest structures need dark matter's scaffolding, or just a rewrite of physics' oldest rules. But the plot thickens. Dark matter proponents counter that Tucana's quirks might stem from its environment, a rare confluence of filaments and voids that warp its motion in ways simulations struggle to replicate. They argue that tweaking dark matter distributions or accounting for undiscovered nearby mass could resolve the discrepancies without overhauling gravity itself. The debate isn't just academic, it cuts to the core of how we understand the cosmos. If Tucana favors it could upend decades of astrophysics. If dark matter adapts, it reinforces its role as the universe's hidden architect. What's fascinating is how Tucana's isolation plays into this drama. Unlike superclusters drowned in the cosmic web's noise, Tucana sits relatively alone, its dynamics unpolluted by neighboring giants. This simplicity makes it a cleaner laboratory, a place where theories can't hide behind complexity. Every anomalous galaxy, every skewed velocity is a clue whispering secrets about gravity's true nature. Yet the most humbling thought, Tucana's light reaches us from an era when the universe was younger, its galaxies caught in a snapshot of their ancient selves. By now, their dance may have changed, their motions veering closer to one theory or the other. But for us, they remain frozen in this moment, a cosmic riddle waiting to be solved. Whether Tucana heralds a revolution in physics or just a footnote in dark matter's dominance, It reminds us that the universe's largest structures aren't just wonders to behold. They are puzzles to crack, each one holding keys to truths we've yet to uncover. At the heart of the Hydra Centaurus supercluster lies one of the universe's most perplexing gravitational anomalies. The Great Attractor, a region so dense with galaxies that it bends the very fabric of space around it. Picture a whirlpool in the cosmic ocean, silently dragging everything in its vicinity toward an unseen center. This 100 million light-year core doesn't just host galaxies, it hoards them, packing thousands into a relatively small volume. Their combined gravity warping the paths of entire superclusters, including our own Milky Way, which hurtles toward it at over 600 kilometers per second. What makes this region so baffling isn't just its pull, it's how much of it remains hidden. The Great Attractor sits directly behind the zone of avoidance, a stretch of sky obscured by the Milky Way's dust and stars. For decades, it was like trying to study a mountain range through a blizzard. We knew something massive was there, but its details were blurred beyond recognition. Only with advances in infrared and radio astronomy tools that peer through cosmic fog have we begun to untangle its secrets. The images that emerged revealed a chaotic metropolis of galaxies, many colliding and merging in a gravitational frenzy, their starlight distorted by dark matter's invisible scaffolding. But here's the twist: the Great Attractor isn't the end of the story. Its gravity alone can't fully explain the velocities we observe. Galaxies here are moving too fast, as if something even larger, something beyond our current maps, is pulling them. That's where the Shapley supercluster comes in, a colossal mass 800 million light-years farther away, acting like a cosmic anchor. Together, these two titans form a gravitational conveyor belt, with the Hydra Centaurus core serving as the midway point, a whirlpool in a much vaster river. Yet the mysteries don't stop there. The Great Attractor's core defies expectations with its uneven distribution of galaxies. Some clusters are packed so tightly they share halos of hot gas, while others float in eerie isolation, their orbits suggesting they're newcomers caught in the act of falling in. This imbalance hints at a violent history, perhaps a past collision with another supercluster, or the lingering echo of primordial density fluctuations from the universe's infancy. The most haunting realization: we're seeing this core as it was 100 million years ago. By now, its galaxies may have merged into even larger giants or been flung outward by dark energy's push. But for us, it remains frozen in time, a gravitational puzzle, a cosmic siren call, and a reminder that even the universe's most powerful forces can hide in plain sight, just beyond the edge of our vision. The universe has an unspoken rule, a limit to how big things can get. Buried in the math of cosmic evolution lies a theoretical boundary, 1.2 billion light-years, the scale at which the universe stops forming structures entirely. Beyond this point, gravity's reach is simply too weak, stretched thin by the relentless expansion of space. That means every titanic wall, every sprawling supercluster we've explored, from the Hercules-Corona Borealis Great Wall to the Shapley supercluster, exists on borrowed time. They're the last of their kind, cosmic dinosaurs in an era where dark energy dominates and the universe grows ever colder. This limit isn't arbitrary. It's woven into the fabric of cosmology itself. In the early universe, tiny quantum fluctuations smaller than atoms seeded the first ripples in matter's distribution. Over billions of years, gravity amplified those ripples, sculpting them into galaxies, clusters, and the filaments of the cosmic web. But here's the catch: gravity works slowly and dark energy works fast. As the universe expands, structures still forming get torn apart before they can reach colossal scales. The 1.2 billion light-year mark is the tipping point, the moment when dark energy's push overwhelms gravity's pull, freezing the cosmic web in place. What's humbling is how close some structures come to breaking this rule. The Hercules-Corona Borealis Great Wall stretches 10 billion light-years, but it's not a single coherent object. It's a statistical ghost, a pattern of galaxies aligned by chance. True physical structures bound by gravity can't grow that vast. Even the Shapley supercluster, the largest confirmed mass concentration, is just a speck compared to this ultimate limit. It's like the universe issued a cosmic speed limit, and every giant we've found is racing against it. The implications are profound. It means we're living in a golden age of cosmic architecture, a fleeting window where structures this grand can exist. In the far future, trillions of years from now, dark energy will stretch space so thin that even superclusters will dissolve, their galaxies isolated like ships lost in an endless ocean. The universe will forget how to build giants, leaving only echoes of what once was. So when we marvel at these titanic structures, we're not just seeing the universe's past, we're glimpsing a vanishing act. They're the final masterpieces in a gallery that will never grow larger, the last whispers of gravity's golden age before silence takes hold, and that makes them more than cosmic curiosities. They're relics of a universe that once knew how to dream big. From the Hercules-Corona Borealis Great Wall, stretching 10 billion light-years like a crack in the cosmic egg, to the Boots Void, where emptiness itself spans 330 million light-years, these titanic structures don't just defy imagination, they rewrite the rules of reality. Imagine standing on a shoreline, watching waves roll in, only to realize each wave is larger than 1,000 Milky Ways, and the ocean stretches farther than time itself. That's the scale we're grappling with. These aren't just objects, they're the universe's architecture, woven from dark matter and starlight, assembled by gravity's patient hand over billions of years. Yet every discovery raises more questions than answers. How does something as vast as the giant arc, 3.3 billion light-years of perfectly aligned galaxies, exist when our best models say it shouldn't? Why does the cold spot, a cosmic bruise in the afterglow of the Big Bang, match up eerily with the Eridanus supervoid, a billion light-year shadow in space? These aren't just puzzles, they're cosmic rebellion, evidence that the universe operates on scales and principles we're only beginning to glimpse. Every time we think we've mapped the limits of structure, the cosmos laughs and shows us another layer. And here's the thrilling thought, we've only scratched the surface. Our telescopes see just a fraction of the sky, and even then, only in narrow slices of time. Beyond the horizon of our observable universe, beyond the reach of light that will never reach us, who knows what other giants loom? Structures so vast they make the Hercules-Corona Borealis wall look quaint, voids so empty they redefine the meaning of nothingness. The universe loves to surprise us, and every anomaly, every unexplained drift of galaxies is a clue that there's more, so much more, waiting to be found. So as we wrap up this journey through the cosmos' grandest designs, I want to leave you with this. The universe isn't just bigger than we imagine, it's stranger. And the best part, we're just getting started. If your mind's as blown as mine is, hit that like button, it helps others discover these cosmic wonders. Subscribe to join us as we keep unraveling space's greatest mysteries, and drop a comment below. What cosmic structure fascinates you the most? A supercluster? A void? Something even wilder? Let's keep exploring together, because out there, in the dark between the stars, the universe is still dreaming up giants.